Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at the phenomenon of light, the energy that reveals every shape, color, and horizon we know. This story is designed to help you learn while you rest. If sleep doesn't come right away, that is completely fine. You can still enjoy learning interesting scientific facts before sleep. Simply listen, let your breathing slow, and allow the information to settle at its own pace. Light is both the most familiar and the most mysterious feature of our world. It outlines the landscape each morning, marks the rhythm of our days, and hides again when night returns. Every glance you take, every color you recognize, depends on it. Yet, for all its presence, light has a nature that defies ordinary logic, behaving as wave and particle, instant and ancient, soft and immense all at once. From the glow of a nearby lamp to the shimmer of a distant galaxy, light defines what we can know. It paints the surfaces of oceans and leaves, threads through air and glass, and carries signals across space. Without it, there would be no vision, no photosynthesis, no warmth from the sun. Every living thing, from single cells to human eyes, is tuned to its presence. Scientifically, light is a narrow slice of the electromagnetic spectrum, a continuum of energy waves that includes everything from radio transmissions to gamma radiation. Our eyes detect only a small portion of that range, centered perfectly where Earth's atmosphere allows most radiation to pass through. Evolution favored sensitivity to these wavelengths because they dominate the sunlight reaching the planet's surface. In that sense, we are literally adapted to the color of our world. But beyond its measurable properties, light carries deeper meaning. It marks beginnings and endings. It signals safety and discovery. Its return after darkness has inspired myths of creation, rebirth, and clarity for thousands of years. The very word enlightenment reflects how knowledge and brightness intertwine. When we study light scientifically, we also explore an ancient human symbol for understanding itself. Consider how light behaves in your daily surroundings. A beam passing through a window reveals dust suspended in air, tiny particles rendered visible only because light scatters from them. A polished surface mirrors the room, while a rough one diffuses the reflection into softness. Through such ordinary events, the laws of physics express themselves quietly. Light never rests, never hesitates. It travels in straight lines until something bends or absorbs it, then moves on again. As we begin this journey, imagine light not as a single beam, but as a presence woven through everything. Picture sunlight spilling over mountains, the faint blue of the sky that encloses us, the minute sparkle caught on the edge of a glass of water. These are fragments of one vast phenomenon connecting the sun, the earth, and every eye that opens to see. Our exploration will move from the birth of light in the early universe to its roles in art, medicine, and the human spirit. Along the way, we will find that the science of light is also a story of perception, time, and transformation. It is the thread linking the cosmic with the personal, a bridge between the stars and the small circle of radiance around you now. So, as you settle into stillness, let the concept of light unfold at its own calm rhythm. You do not need to remember every detail or follow every number. The facts will drift gently through your awareness, each one a quiet spark joining the next. Light surrounds you even now, in the faint glow of your room, in the memory of day, in the particles moving unseen beyond your sight. It has been here since the beginning and will continue long after. And with that thought, our journey begins. To understand light, we must begin at the moment when it first appeared. There was a time when no star had yet formed, when the cosmos was so dense and hot that matter and energy could not exist separately. In those earliest instants after the Big Bang, the universe was a uniform ocean of charged particles and radiation, a glowing fog where photons could not travel freely. Every attempt a photon made to move was interrupted almost instantly by collisions with electrons and protons. The universe was bright in energy but dark in transparency. As space expanded, this seething mixture began to cool. Within the first few 100,000 years, temperatures dropped enough for protons and electrons to combine, forming the first hydrogen atoms. That simple act, the binding of a nucleus and an electron, changed everything. Once atoms existed, photons no longer scattered incessantly. They were released, finally able to travel without being trapped. In that instant, light as we know it began its journey through space. The cosmos, once opaque, became transparent. This transformation is called recombination, though it was really the first great separation. Matter on one side, radiation on the other. The flood of photons that escaped then has never stopped moving. Over billions of years, the stretching of space has lengthened their wavelengths, turning the once dazzling glare into faint microwave radiation. Yet it still fills the universe today, an all-pervasive whisper known as the cosmic microwave background. When scientists map this background, they are not looking at stars or galaxies, but at the afterglow of the universe's birth. Sensitive instruments aboard satellites such as COBE, WMAP, and Planck have captured subtle temperature variations, differences of less than a few millionths of a degree. Those tiny ripples are fossils of the first irregularities in density, the seeds from which galaxies and clusters eventually grew. Each variation marks a place where matter was just slightly more concentrated, where gravity would later draw material together to ignite the first stars. Imagine standing, in thought, within that young universe. There is no direction, no shape, only expansion. The light is not yet visible color but pure radiation, streaming evenly through newborn space. Every photon is a messenger from that origin, carrying with it a record of the moment the fog cleared. When we detect this background today, we are in effect touching that ancient time. The signal has crossed more than 13 billion years to reach our antennas and telescopes, its energy softened but its story intact. The release of light marked the transition from chaos to structure. Once photons could move unhindered, they began to trace the geometry of the universe, defining distances and allowing matter to gather. Temperature fell, hydrogen clouds formed, and gravity quietly sculpted the next stage, the first stars. Light did not merely illuminate creation, it enabled creation, turning the opaque into the observable. This origin also reminds us that light is inseparable from time. The photons arriving at this very moment are survivors of that first freedom. They have never slowed, never aged, simply continued along the stretching fabric of space. The glow that surrounds the cosmos is therefore both ancient and immediate, a living relic of beginnings that continue to influence us. Think of it as the universe taking its first clear breath, the moment when it became possible for information to travel, for vision eventually to exist, and for observers like us to appear. What began as radiation imprisoned in plasma became the light that still defines reality. Every lamp, every sunrise, every reflection in glass is a descendant of that release. From that primal emergence, the story of light expands outward. In the ages that followed, new sources would ignite, scattering brightness across the growing universe. But everything that came later, every color, every shadow, every spark, traces back to that first liberation, when light escaped the fog and the cosmos became transparent. It was the beginning not only of illumination, but of sight itself. Even now, more than 13 billion years after its birth, the universe still glows with the memory of that first light. This glow is not bright to the human eye. In fact, it lies far beyond what we can perceive, but it fills every direction with quiet uniformity. Scientists call it the cosmic microwave background, or CMB. It is the faint radiation that remains from when the universe first became transparent, a relic older than any star, older than the galaxies themselves. When we look at the sky today, most of what we see comes from stars that shine within the last few billion years. The CMB, however, comes from a time only about 380,000 years after the Big Bang, the moment when atoms first formed and photons were released. That radiation has been traveling ever since, stretched and softened by the expansion of space. What was once blinding white heat is now cooled to a temperature just above absolute zero, about 2.7 kelvins. Its wavelength has lengthened from visible light into microwaves, invisible but measurable by instruments designed to detect it. To capture this whisper of ancient light, scientists have launched satellites that rise above Earth's atmosphere, where interference from ground radiation fades away. The first such mission, COBE Cosmic Background Explorer, launched in the late 1980 seconds, confirmed the perfect black-body curve of the CMB, the signature of a thermal origin. Later, WMAP and Planck refined the picture with extraordinary precision, revealing delicate variations in temperature. These small differences, no greater than a few parts in 100,000, form a cosmic fingerprint. They show where matter was slightly denser or thinner in the early universe, the seeds of everything that would later emerge. Those variations can be thought of as ripples in a vast ocean of energy. Over time, gravity amplified them. Regions slightly richer in matter attracted more material, eventually giving rise to stars, clusters, and galaxies. Without those faint irregularities, everything might have remained evenly spread, a universe without form or structure. The CMB is thus both a record and a reason for the cosmos we now inhabit. If your eyes could see in microwaves instead of visible light, the night sky would not appear dark at all. It would shimmer evenly in every direction, a pale map of temperature with tiny mottled patterns. Each spot of slightly higher warmth represents a place where matter was a little thicker, where gravity began to do its slow work. In this way, the background radiation is not merely an echo but a blueprint. It is also astonishingly uniform. No matter where astronomers aim their detectors, across galaxies, through voids, past the Milky Way, the same faint signal appears. This near-perfect evenness suggests that the early universe was once in close communication with itself, smoothed by a brief but immense period of inflation. That rapid expansion linked distant regions so thoroughly that they still share the same temperature to a remarkable degree. Every photon of the CMB has traveled unbroken since that primordial moment. It has crossed expanding space, passed through forming galaxies, slipped between stars, and reached us without rest. When our instruments register its presence, we are effectively touching time itself. The data are not a simulation or an inference. They are direct measurements of ancient light still arriving. There is something quietly profound about this realization. Even in the deepest darkness of space, the universe carries its own background glow, a soft and persistent memory of its youth. It is not visible starlight or scattered reflection, but the first light ever set free. When we detect it, we are witnessing the universe remembering itself. Imagine, then, this constant radiation as a steady tone, a hum too faint for ears but present everywhere. It does not fade or stop. It continues through every atom, through your body, through the ground beneath you. It is the earliest light, stretched by time, still moving, still speaking of beginnings. To understand it is to recognize that the universe, though vast and ancient, remains connected across its history by this single, enduring glow, the gentle echo of the moment when light first learned to travel. After tracing light back to its cosmic origin, we now turn to its behavior, the language it uses to move through space. For centuries, scientists struggled to describe what light actually is. They knew it could be reflected, refracted, and scattered, yet it seemed to behave like both substance and motion. The key to understanding came with the realization that light travels as a wave, a repeating pattern of energy that flows through the emptiness between atoms and stars. To imagine a wave, think of how energy moves across the surface of a calm sea. A crest rises and falls, carrying rhythm forward, even though the water itself remains in place. Light behaves in a similar way, but instead of water molecules, it ripples through electric and magnetic fields. These fields oscillate at right angles to one another, dancing together through space in perfect synchrony. That is why we describe light as an electromagnetic wave. Every wave has two defining traits: its wavelength, the distance between one crest and the next, and its frequency, the number of crests passing a point each second. These two quantities are inversely related. The shorter the wavelength, the higher the frequency, and vice versa. In light, these variations determine color. Red light has relatively long wavelengths, while violet vibrates far faster, its waves packed tightly together. All the colors we see occupy a narrow band of frequencies, nestled between infrared and ultraviolet radiation. The full electromagnetic spectrum extends far beyond what human eyes can detect. At one extreme are radio waves, with lengths that can stretch for kilometers. At the other, gamma rays, whose wavelengths are smaller than an atom. Yet the behavior is the same, rhythmic oscillations carrying energy outward. The only difference is scale. Our eyes evolved to sense the range most abundant on Earth's surface, the sunlight that passes most efficiently through our atmosphere. When we examine light as a wave, many of its seemingly mysterious effects become clear. A mirror, for instance, simply redirects the wavefronts. A lens bends them by slowing their speed inside glass. Waves can overlap and interfere, combining in complex patterns that create bright or dark regions. Two waves in step will add together, producing brilliance. Two out of step will cancel, leaving shadow. This principle explains much of the beauty we encounter daily, from the iridescent sheen of soap bubbles to the subtle hues of a butterfly's wing. The wave model also reveals why light can spread and bend around obstacles, a process called diffraction. When a wave passes through a narrow opening, it fans outward instead of continuing in a straight line. The edges become sources of new waves, softening shadows and creating delicate fringes of light and dark. Even without realizing it, we witness diffraction every time sunlight filters through a curtain and projects faint bands across a wall. Understanding light as a wave connects the microscopic and the immense. The same mathematics that describe radio signals between satellites also explain the faint glow of starlight crossing intergalactic space. Whether the wavelength measures meters or nanometers, the pattern endures. Energy oscillating between electric and magnetic forms, racing at the constant speed of light. If you were to picture this process, imagine an endless ocean of invisible ripples stretching in every direction. There is no surface and no shore, only the quiet repetition of rise and fall, crest and trough. Each wave travels onward without fatigue, passing through the void as effortlessly as a thought. You are surrounded by this motion always, waves of every size, crossing, merging, separating, the universe alive with vibration. Recognizing light as a wave was one of humanity's great steps in grasping nature's unity. It taught us that color, warmth, and radio communication are all expressions of a single phenomenon, oscillations of the same field that fills all of space. From this foundation, the next questions arise: how waves interact, how they create color and pattern, and how light's rhythm shapes the world we see. Once scientists understood that light behaves as a wave, they began to explore how those waves interact. The discovery that light could combine, reinforce, or even cancel itself changed our understanding of the world's colors and textures. This interplay, called interference, revealed that light is not only motion but also structure, capable of producing beauty and information through rhythm alone. To grasp interference, imagine two sets of ripples meeting on a pond, where the crests of one align with the crests of the other. The waves grow taller. Where a crest meets a trough, they flatten and disappear. Light follows the same rule. When two beams overlap in space, their electric and magnetic fields add together. At some points they strengthen, at others they weaken. The result is a pattern of brightness and shadow, a visible record of how waves meet. This phenomenon was demonstrated most clearly in the double-slit experiment. When a beam of light passes through two narrow openings, it doesn't create two distinct spots on the wall beyond. Instead, it forms a series of alternating bright and dark bands, the direct imprint of interference. That pattern proves that light spreads as waves, each slit acting as a source that radiates outward. Where the waves coincide, they shine. Where they oppose, they fade. Interference is not an abstract curiosity. It surrounds us in daily life. The shifting rainbow colors on a thin film of oil, or the delicate hues on a soap bubble, appear because layers of different thicknesses cause light waves to overlap unevenly. Some wavelengths reinforce, others cancel, and the result changes with every angle. Even the blue of the sky arises from how shorter wavelengths scatter more effectively through the molecules of air, filling the atmosphere with soft diffusion. Every tint and shimmer you see owes something to the way light waves mix and scatter. The natural world has long exploited these principles. The feathers of peacocks and the wings of butterflies contain microscopic structures that split and recombine light, creating iridescence without pigment. The surfaces of seashells and minerals do the same. Their colors shift with viewing angle because the waves reflected from different layers change phase, sometimes merging, sometimes subtracting. In each case, light's interference becomes art, turning physics into pattern. Scientists learn to use this behavior deliberately. Instruments like spectrometers and interferometers rely on controlled interference to measure distances and wavelengths with extraordinary precision. In astronomy, interference from multiple telescopes can be combined to produce images far sharper than any single mirror could achieve. On Earth, thin films are designed to minimize reflection in camera lenses or to enhance it in anti-counterfeit holograms. What began as a discovery of simple ripples has become one of the most powerful tools of observation. There is also poetry in this behavior. Light, when left to itself, travels evenly and invisibly, but when paths cross, new designs appear: bands, colors, rings, and halos. From interaction comes meaning. Even in the stillness of a dark room, light from two tiny openings can weave a tapestry of contrast across a surface. Every interference pattern is a silent map of how waves share space. If you picture the universe as filled with light, you can imagine these countless overlaps happening everywhere, continuously. Waves from stars, from lamps, from reflections off walls and water, all blend and recombine. The air around you is a quiet orchestra of these interactions, each vibration contributing to a chorus that defines color and clarity. Interference reminds us that complexity and beauty arise from cooperation. No single beam produces a rainbow or a shimmer on the sea. It takes many meeting at just the right angles to create the spectacle we see. Light's waves show that harmony and contrast coexist, that even the simplest laws of physics can produce endless variation. And as those invisible patterns move across space, they link everything touched by light into a single, continuous field of motion. After centuries of studying light as a wave, another truth emerged, one that seemed to defy reason. Experiments revealed that light sometimes behaves not like a continuous ripple, but as if it were made of countless tiny packets of energy. These packets are called photons, and they reshaped the entire field of physics. From this point on, scientists had to accept that light can act as both wave and particle, depending on how it is observed. The story began with the photoelectric effect. In the early 20th century, researchers found that shining light on certain metals could knock electrons free from their surfaces. The mystery was that brighter light did not always free more electrons, and the color of the light mattered more than its intensity. Classical wave theory could not explain this. It predicted that the energy should depend only on brightness, not on wavelength. It was Albert Einstein who solved the puzzle. He proposed that light arrives in discrete quanta, each photon carrying a specific amount of energy determined by its frequency. The higher the frequency, the more energetic the photon. Blue light carries more energy than red, and only photons above a certain threshold can liberate electrons. This insight did more than explain a laboratory anomaly. It gave birth to quantum theory, the foundation of modern physics. It revealed that the universe is built not from smooth continuities but from indivisible units, quanta, of which photons are one form. For this discovery, Einstein received the Nobel Prize in 1921. His work showed that energy and matter are intertwined, and that even something as intangible as light follows rules of discrete exchange. The particle nature of light is evident all around us. Every time sunlight strikes a leaf, photons are absorbed by molecules of chlorophyll, setting off the reactions of photosynthesis. In a solar panel, photons strike silicon atoms and release electrons that flow as current. In a digital camera, photons hit tiny sensors, each impact recorded as a pixel of brightness. These are not waves washing over a surface, but individual quanta transferring energy, one event at a time. Photons are strange entities. They have no mass, no size that can be measured, and they never rest. Each one travels at the constant speed of light, regardless of where or when it was emitted. A photon released from a distant star will cross space for billions of years without slowing or changing its energy, unless stretched by the expansion of the universe itself. When it finally reaches your eyes, it tells a story that began before Earth existed. Despite their ghostly nature, photons obey the logic of particles. They can collide with atoms, be scattered, absorbed, or emitted. Yet they also remain inseparable from the wave patterns that describe their motion. Physicists often speak of this as wave-particle duality, not two separate forms, but two ways of understanding one phenomenon. Depending on how we look, light can appear as an undulating field or as a stream of discrete impacts. Both are true, and together they describe reality more completely than either alone. This duality still fascinates scientists. In laboratories, single photons can be detected one by one, each leaving a tiny signal on a sensor. Yet when many are allowed to pass through the same apparatus, they collectively form interference patterns, behaving like waves once again. It is as if each photon knows about all the paths it could take and chooses among them probabilistically. At human scales, this seems paradoxical, but at the quantum level it is nature's most reliable law. If you imagine photons visually, think of them as small bursts of energy darting through the dark, countless messengers moving in all directions. Each carries a quantum of information about its source, its color, and its path. Billions strike the Earth every second, bathing everything in light without ever adding weight. They are the reason you can see, the reason plants grow, the reason solar energy exists. Light as particles reminds us that continuity and discreteness coexist in the same world. What seems like a smooth beam is actually a swarm of microscopic events, each one essential, each one fleeting. In that sense, light is both rhythm and pulse, the music of waves made tangible through the smallest units of energy. Among all the constants in the universe, one number stands apart: the speed of light. It is the ultimate limit, a boundary that no signal, object, or piece of information can cross. In a vacuum, Light travels at nearly 300,000 kilometers each second. That means it can circle the Earth more than 7 times in a single heartbeat. But this immense speed is more than a measure of quickness. It is the foundation on which the structure of space and time is built. The first measurements of light's speed were made centuries ago. In the 17th century, Ole Rømer, a Danish astronomer, observed slight delays in the eclipses of Jupiter's moons depending on Earth's position in its orbit. From those differences, he realized that light must take time to travel from place to place. Later, more precise experiments confirmed that this velocity is fixed and universal. Whether emitted by a candle or a quasar, light always moves at the same pace in empty space. Nothing can make it go faster, and nothing with mass can reach it. This constancy became the cornerstone of Albert Einstein's theory of relativity. He proposed that the laws of physics must look the same to all observers, no matter how fast they move, and to preserve that symmetry, the speed of light must be invariant. The consequences of this idea are profound. Time and space, once thought to be separate and absolute, turn out to be interwoven. When an object moves close to light speed, its passage of time slows compared with that of a stationary observer, and distances in the direction of motion appear to contract. Light, in effect, defines how the universe connects space and time. Relativity also revealed the most famous equation in science, E equals mc squared, showing that energy and mass are equivalent, linked by the square of the speed of light. That enormous number, 300,000 kilometers per second squared, transforms a small amount of matter into vast energy. The sun's brilliance, nuclear reactions, and even the glow of a burning candle all trace back to this principle. It tells us that light is not simply a traveler through space, but a measure of how reality converts between form and energy. Because light has a finite speed, it acts as a kind of cosmic clock. When you look at the moon, you see it as it was about 1.25 seconds ago. Sunlight that warms your face left the sun more than 8 minutes earlier. The starlight visible on a clear night may have begun its journey thousands or even millions of years before reaching your eyes. The farther you look into space, the further back in time you are seeing. Astronomy is, in essence, an act of time travel conducted through light. Even the concept of now becomes relative when distances are large. Two events separated by light years cannot be said to occur simultaneously for all observers, because the signals that connect them travel at a limited pace. Light sets the rhythm of causality, the rule that nothing can influence something else faster than this universal limit. Every event, from the flicker of a lamp to the explosion of a distant star, follows this same constraint. For everyday life, this may seem irrelevant, yet the speed of light shapes technologies we rely on constantly. Communication with spacecraft across the solar system involves delays ranging from minutes to hours. GPS satellites must account for relativistic effects, the difference in time experienced by clocks in orbit compared with those on Earth. Even the synchronization of computer networks depends on knowing precisely how long it takes a pulse of light to move through optical fibers. There is a quiet beauty in this constancy. The speed of light does not vary with time, temperature, or circumstance. It is a thread running through every equation that describes the universe. You might think of it as a heartbeat for reality itself, steady, unchanging, defining the rhythm by which everything else moves. To grasp that every beam, from every star and every lamp, travels at exactly the same pace, is to glimpse the unity of nature. Light's speed connects the vast and the small, the ancient and the immediate. It ensures that the story of the cosmos unfolds in order, bound by a limit that is not a restriction but a structure, the pace at which the universe reveals itself. At first glance, white light seems simple, a steady, uniform glow pouring from the sun or a lamp. Yet within that apparent simplicity hides a magnificent complexity. White light is not a single color at all, but a blend of countless wavelengths woven together. When separated, it unfolds into the familiar rainbow, a visible manifestation of light's inner structure known as the spectrum. The first person to reveal this hidden composition was Isaac Newton in the 17th century. He allowed sunlight to pass through a glass prism and saw it fan out into bands of red, orange, yellow, green, blue, and violet. The prism did not create these colors. It merely separated what was already there. Each wavelength bends or refracts by a slightly different amount as it enters and exits the glass. The shorter the wavelength, the greater the bending. Thus, violet deflects more sharply than red, and the continuum of visible light unfolds before our eyes. Each color corresponds to a specific wavelength, ranging from roughly 700 nanometers for red down to about 400 for violet. These differences may seem minute, yet they define the richness of the world around us. The hues of a sunset, the green of leaves, and the blue of distant mountains all arise from variations in how objects absorb and scatter particular wavelengths. What we perceive as color is the visual record of light interacting with matter. Beyond its beauty, the spectrum carries information. When astronomers spread the light from a distant star through a prism or diffraction grating, they see not just color but patterns, thin, dark lines that mark where atoms in the star's atmosphere absorb certain wavelengths. Each element leaves its own signature, a kind of barcode written in light. By reading those lines, scientists can determine a star's composition, temperature, and even its motion. Light, in this way, becomes a messenger from places we can never reach. The same principle applies closer to home. Every material, from metal to water to paint, reflects and absorbs specific parts of the spectrum. The reason a ripe tomato looks red is that it reflects long wavelengths while absorbing the shorter ones. Snow appears white because it scatters all visible wavelengths equally. Color is thus not a property of objects alone, but a collaboration between light and perception, between photons and the eyes that receive them. Human vision relies on 3 types of cone cells in the retina, each tuned to a range of wavelengths roughly corresponding to red, green, and blue. The brain combines their signals to produce every hue we can imagine. By adjusting the intensity of these 3 components, it constructs the full palette of visible color. This biological system is why electronic screens can reproduce vivid images using only mixtures of red, green, and blue light. They directly stimulate the same receptors that natural light does. Nature, too, plays with the spectrum in creative ways. When sunlight strikes raindrops, each droplet acts as a tiny prism, bending and reflecting light to form a rainbow. The geometry of water and the observer's position determine the arc and order of colors. No 2 people ever see exactly the same rainbow, because each eye receives light from a slightly different set of droplets. In every case, though, the physics is the same: refraction spreading wavelengths into sequence, turning the invisible diversity of light into visible wonder. Thinking about light in terms of its spectrum changes how we perceive the world. A shaft of white sunlight no longer seems plain. It is a harmony of frequencies, a silent orchestra of color waiting to be separated. Even shadows are not truly devoid of hue. They carry a subtle tint depending on the light that fills the surrounding air. The spectrum reminds us that what appears unified often hides variety, and that the richness of reality lies within those hidden differences. When you see a rainbow, you are witnessing light revealing its structure, energy divided by wavelength, yet still one phenomenon. In that moment, the sky becomes a lesson in physics and perception. The same sunlight, shaped by geometry and water, transformed into visible music. The spectrum teaches that unity and diversity coexist, that simplicity is often the mask of complexity, and that within the glow of ordinary daylight lies an entire world of color, endlessly unfolding. To understand light fully, one must also consider its counterpart. Darkness is not the enemy of illumination, but its necessary partner. Without darkness, light would have no form, no edge, no contrast. It is the quiet canvas against which brightness draws its patterns. From the interplay between light and shadow arise depth, texture, and the very perception of space. In physical terms, darkness is simply the absence or scarcity of visible photons. Yet even this absence is rarely complete. On Earth, shadows are softened by the scattering of sunlight in the atmosphere, filling even the deepest shade with a trace of blue. True darkness, the total absence of light, exists only in the depths of caves, sealed chambers, or the void between stars. For most of us, the dark is never absolute. It is a gradient, a quieting rather than a void. The human eye is exquisitely adapted to navigate this boundary. When light fades, our pupils widen, and specialized cells called rods take over from the color-sensitive cones. Rods cannot perceive hue but are extraordinarily sensitive to faint illumination. This shift is why the world at night appears in shades of gray and why a dim star can vanish if you look at it directly, but reappear when seen slightly to the side. Your eyes are constantly balancing the competing demands of light and dark, maintaining visibility across an enormous range of brightness. Darkness also defines how we experience light's behavior. A shadow is not a thing but an area where fewer photons arrive. Its sharpness or softness tells us about the size and distance of the light source. The sun, although vast, is so far away that it casts crisp shadows. A cloudy sky, spreading light from all directions, erases them. Partial shadows, known as penumbras, form when only part of a light source is blocked, a subtle zone between brightness and obscurity. It is this blend of precision and softness that gives visual scenes their realism. Astronomical shadows are more dramatic still. During a solar eclipse, the moon passes between Earth and the sun, aligning so precisely that it briefly covers the solar disk. Daylight fades into twilight, temperatures drop, and the sun's outer atmosphere, the corona, becomes visible, glowing like silver fire around the dark circle. For a few minutes, darkness reveals what is normally invisible. When light returns, the world seems transformed, as if both nature and human perception have paused to acknowledge the balance between brilliance and void. Darkness is vital to life itself. Many species thrive only when light retreats. Nocturnal animals hunt, pollinate, and navigate using cues invisible to us, echoes, scents, or infrared traces. Deep in the ocean, where sunlight cannot reach, organisms produce their own glow through bioluminescence, painting the darkness with living constellations. Even plants depend on night, using darkness to regulate growth cycles and to rest their energy systems. For humans, darkness has long held symbolic meaning. It can suggest fear and uncertainty, but also comfort and renewal. The alternation of day and night sets our circadian rhythm, guiding hormones and sleep. Without regular darkness, that rhythm falters. Artificial lighting, though a triumph of technology, can disrupt these cycles if it overwhelms the natural alternation that our bodies expect. The absence of darkness, as much as the absence of light, can bring imbalance. In art and photography, contrast between light and dark, chiaroscuro, shapes emotion and focus. Painters like Caravaggio and Rembrandt used shadow not to hide but to reveal, directing the viewer's gaze and giving scenes weight and mystery. Darkness frames illumination, giving light its voice. If you picture a candle burning in an otherwise dark room, you can sense this relationship. The flame seems alive not because of its brightness alone, but because of the surrounding blackness that allows it to stand out. Remove the darkness, and the flame loses its power to define the space. Light and dark are therefore not opposites but partners, forever entwined in shaping how we see and feel. In every corner of the universe, this partnership persists. Galaxies shine against the deep background of space. Stars are born within clouds of obscuring dust, and the night itself carries faint traces of scattered starlight. Darkness gives the universe dimension, just as silence gives meaning to sound. Without it, there would be no contrast, no rhythm, no sense of wonder. The two exist together, and in their balance lies the harmony of perception. Every point of light in the night sky carries with it a history far older than anything on Earth. When we look upward, we do not see the universe as it is now, but, as it once was, a mosaic of past moments preserved in traveling photons. Starlight is both illumination and record, a physical link between time and distance. To see the stars is to gaze into a layered past stretching billions of years deep. The light from our nearest star, the Sun, takes a little more than 8 minutes to reach Earth. From the Moon, the journey is just over a second, but from other stars, the intervals become immense. The light from Sirius, the brightest star in our night sky, began its journey about 9 years ago. The glow of the Andromeda galaxy, visible as a faint blur through binoculars, has been traveling for more than 2 million years, long before the first humans walked the planet. Each photon that reaches your eye has crossed unimaginable expanses, uninterrupted and unchanged, until it becomes a fleeting spark in your vision. Astronomers measure these vast stretches using the light year, the distance light travels in 1 year, about 9.46 trillion kilometers. This unit is not a measure of time, but of space, defined by time, because distance and duration are inseparable when light is the messenger. When we say a galaxy lies 100 million light-years away, we mean that its light has been traveling toward us for that many years. We are witnessing it as it was when dinosaurs roamed the Earth. As light travels through expanding space, its wavelength stretches. This effect, called redshift, shifts the light toward the red end of the spectrum as the universe expands. The greater the redshift, the farther away and the older the source. By studying these shifts, astronomers can determine how fast distant galaxies are receding, revealing that the universe itself is stretching faster over time. Redshift is therefore not just a change of color but a measure of cosmic history, proof that space is alive with motion. Not all cosmic light shines steadily. Some of the most distant and powerful objects in the universe, quasars, are fueled by supermassive black holes at the centers of galaxies. Their radiation outshines entire galaxies, and yet it too must travel for billions of years before reaching our instruments. Other lights, like those from supernovae, are brief but spectacular, marking the explosive death of massive stars. When their photons finally arrive, they tell us not only about those stars' endings but also about the chemical elements created in those final moments, elements that would later form planets and life. The faintest glimmers we detect come from galaxies so remote that their light has been stretched nearly beyond recognition. Astronomers using long-exposure telescopes capture single photons that may have been traveling for almost the entire age of the universe. These delicate signals confirm that we are still surrounded by the echoes of the earliest structures, the cosmic web of matter that began forming shortly after the first light was released. For all its vastness, starlight is personal too. Every person who has ever looked up has seen the same constellations and wondered at their permanence, unaware that what appears steady is constantly changing. Some of the stars that shine tonight may already be gone, their light still on its way across the gulf. What we see is their lingering presence, an image of what they once were. You can imagine a single photon leaving the surface of a distant sun, racing through vacuum for millions of years. It passes galaxies, nebulae, and clouds of dust, unaffected by what it crosses, until it encounters Earth's thin atmosphere and bends slightly as it enters. Finally, it touches your eye, completing a journey longer than all of recorded history. In that moment, time collapses, the past and present merge in a single instant of perception. Starlight reminds us that the night sky is not a static dome but a living archive. Each twinkle is a relic of an event long gone, a data point in the universe's evolving story. When you look upward, you are not just observing, you are receiving messages written in light, each one a fragment of cosmic memory, still glowing across time. The colors we see with our eyes make up only a narrow band of the electromagnetic spectrum, a thin sliver in an ocean of invisible waves. What we call visible light is simply that portion of radiation to which human vision has evolved sensitivity. Beyond the reds and violets lies a vast, unseen world, filled with forms of light that shape everything from weather and health to communication and astronomy. To understand the true scale of illumination, we must look beyond sight itself. Light is part of a continuum of electromagnetic radiation, where each type differs only in wavelength and frequency. Longer waves carry less energy, shorter ones carry more. Moving downward from visible red, we encounter infrared radiation, then microwaves, then radio waves, with lengths ranging from micrometers to kilometers. Moving upward from violet, we find ultraviolet, then X-rays, and finally gamma rays, whose wavelengths are smaller than the nucleus of an atom. The physical laws governing all of them are identical: oscillations of electric and magnetic fields traveling through space at the same unchanging speed. Infrared light was discovered in 1800 by William Herschel, who noticed that the temperature beyond the red edge of a prism's spectrum was higher than within the visible colors. He had found heat carried by radiation invisible to the eye. Infrared waves are absorbed and emitted by warm objects, which is why thermal cameras can visualize temperature differences as false color images. For animals like snakes or certain insects, infrared is as real as sunlight. They use it to sense prey in darkness or to navigate environments hidden from human sight. To them, warmth glows. Even longer wavelengths form the radio spectrum, discovered by James Clerk Maxwell's equations and demonstrated by Heinrich Hertz. These waves can pass through clouds, fog, and even walls, making them ideal for communication. Radio telescopes, using massive parabolic dishes, capture these signals from the cosmos, unveiling pulsars, quasars, and clouds of hydrogen gas invisible to optical telescopes. Through radio light, astronomers have mapped the spiral arms of our galaxy and detected the faint hiss of the cosmic background radiation itself. Moving in the opposite direction, above violet, the waves shorten and energy rises. Ultraviolet light, discovered by Johann Ritter in 1801, is just beyond human vision, yet profoundly influential. The sun emits large amounts of UV radiation, most of which is filtered by Earth's ozone layer. What does reach the ground initiates essential chemical reactions. It triggers the production of vitamin D in skin but can also damage DNA, leading to sunburn or cancer. Plants and insects have adapted to these wavelengths in remarkable ways. Many flowers display ultraviolet patterns, invisible to us but visible to bees, acting as guides toward nectar. To a bee, a simple daisy is a radiant target, painted with invisible arrows of light. Even higher in energy come X-rays, discovered accidentally by Wilhelm Röntgen in 1895, when he observed that certain rays could pass through solid materials and cast shadows of bones on photographic plates. This revelation transformed medicine and later astronomy. Today, space telescopes equipped with X-ray detectors reveal the violent environments around black holes and neutron stars, where temperatures soar into the millions of degrees. Without X-rays, much of the high-energy universe would remain hidden. At the extreme end lie gamma rays, the most energetic form of light. They are produced in radioactive decay, supernovae, and the collisions of subatomic particles. Some of the brightest flashes ever recorded, gamma-ray bursts, occur when massive stars collapse or when neutron stars merge. For a few seconds, a single event can outshine the combined light of all galaxies in the observable universe. These bursts, though deadly if nearby, provide clues about the birth of elements and the most extreme physics known. Human technology has learned to harness nearly every part of this spectrum. Microwave ovens heat food by exciting water molecules. Radio antennas send voices across oceans. Fiber optic cables carry streams of digital data encoded in pulses of infrared light. Medical imaging uses X-rays to look inside the body. Security scanners employ terahertz waves, and astronomers observe gamma rays to study cosmic explosions. Each portion of the spectrum offers a new sense, a new way to read the universe. If you could perceive all these forms at once, the world would appear utterly transformed. The night sky would blaze with invisible radio and X-ray light. Every warm surface would shimmer with infrared. Cosmic rays would streak across your view. What seems dark to us is in fact saturated with radiation. Our eyes evolved to see only the range that matters most for survival, but the universe radiates across a scale so wide that human perception captures less than a billionth of it. To move beyond visible light is to realize that darkness is an illusion of biology. The air around you is alive with unseen signals, phone transmissions, Wi-Fi, microwaves, and starlight stretched into long waves by cosmic expansion. All are forms of the same phenomenon, traveling together through space. They whisper constantly, carrying energy and information from near and far. Light, in all its forms, is the silent architecture of the universe, unseen, unending, and always present, whether or not our eyes are able to notice it. After traveling through theories, spectra, and distances measured in billions of years, it helps to stop and simply look upward. The night sky is not only a subject of study, it is an experience, a shared view that has connected humans across time. To pause under the stars is to stand inside the story of light itself, surrounded by its sources, bathed in its quiet messages, and reminded of our place in the immense continuum of space. On a clear, moonless night far from city glow, the sky appears dense with points of brilliance. Yet most of those stars are not particularly bright. They are simply unobscured by atmospheric haze and artificial light. The human eye, when fully adapted to darkness, can detect thousands of stars without aid, and even faint smudges of the Milky Way, our galaxy seen edge on. That ribbon of hazy light is not a cloud at all, but the combined glow of hundreds of billions of suns whose collective radiation merges into a luminous stream. When you look at it, you are viewing the disk of our home galaxy from within, peering through its thin plane as it wraps around you. The atmosphere plays a constant role in how we see this spectacle. Starlight passing through layers of moving air is bent ever so slightly, causing stars to appear to twinkle. This scintillation is not a property of the stars themselves, but of the living, breathing sky above us. Each tiny fluctuation in temperature or density refracts light differently, making stars flicker as though they were alive. From the surface of space, above the atmosphere, they shine steadily, unwavering, like distant beacons. Different colors of starlight tell us about their temperatures. Red stars glow more softly, radiating at cooler levels of a few thousand degrees. Blue stars burn fiercely at tens of thousands. When we see color among the stars, we are perceiving their thermal history, an entire astrophysical biography condensed into a shade. Astronomers analyze those hues to determine chemical composition, density, and age. A single glimmer can tell the story of hydrogen fusing into helium, of elements being forged and released into future worlds. Between those bright points lies more darkness than light. Yet even the apparent emptiness of space is far from void. The background of the sky, invisible to naked vision, hums with radio waves, X-rays, and microwaves, the remnants of ancient light, the signals of galaxies, the soft afterglow of the Big Bang. To stand beneath the stars is to stand within this flood of radiation, though we sense only the faintest visible fraction. The stillness of night hides a storm of motion and energy invisible to our eyes. Our relationship with the night sky is older than civilization. Long before telescopes or written records, early humans charted the heavens, finding order in repeating patterns. They saw constellations rise and fall with the seasons and used them to guide migrations and harvests. The stars served as calendars, compasses, and storytellers. Even now, their ancient light continues to mark time for us, though our instruments are more precise. Observing the sky connects us to the same curiosity that drove our ancestors to wonder what those distant fires meant. From a scientific perspective, each star is a nuclear furnace, sustaining itself through fusion, the joining of atoms that releases extraordinary energy. The Sun follows this same rule, transforming 4 million tons of hydrogen into light every second. That light, filtered through Earth's atmosphere, is the reason the night exists at all. Even darkness is defined by light's absence, a reminder that one cannot be known without the other. For astronomers, a night under the stars is not just beautiful but instructive. They measure positions, brightness, and spectra. They observe motion that reveals planets orbiting invisible suns. Yet beyond the data, there remains awe, an emotion unconfined by equations. Many scientists describe moments when observation gives way to stillness, when the magnitude of what they study outweighs the need to explain. Beneath that canopy of radiance, intellect and wonder coexist. If you were to lie on your back now and simply look up, you would become part of a long human ritual, quiet observation of light that has traveled across impossible distances to reach your eyes. The photons falling on your retinas may have begun their journey when continents were still forming or when civilizations had yet to exist. Each one concludes its ancient voyage in a brief instant of sight. The connection between observer and cosmos becomes literal. You are completing an event that started eons ago. To pause under the stars is to let that awareness settle. It requires no telescope, no equations, no urgency. The science is there, in the color of the stars, the motion of the air, the absorption of wavelengths, but it is joined by something simpler, perspective. You are a witness to the ongoing conversation between matter and energy, between light and time. In that recognition, quiet understanding replaces analysis. The universe, vast and intricate, continues its rhythm above you. The stars shimmer not to demand comprehension, but to remind you that you are already part of the same luminous design. Whenever light encounters a surface, it must decide whether to turn back or move through. These two responses, reflection and refraction, are among the most fundamental interactions in physics. Together, they shape almost everything we see. The glint of a lake, the shimmer of glass, the sparkle of a gem, and even the clarity of our vision. Without these twin behaviors, light would not form images, and the world would appear without boundaries. Reflection occurs when light bounces off a surface rather than entering it. The rule is simple and precise. The angle of incidence equals the angle of reflection. This law applies to everything from a mirror to a moonlit sea. When light strikes a smooth surface, the reflected rays remain organized, forming a clear image. This is called specular reflection. But when light hits a rough or irregular surface, it scatters in many directions, creating diffuse reflection, which allows us to see most ordinary objects. A wall, for example, reflects light diffusely, so we perceive its color and texture, but not our own image upon it. The distinction between specular and diffuse reflection explains much of what we intuitively recognize as shiny or matte. Polished metal, glass, and water reflect light coherently, producing sharp highlights. Wood, cloth, and stone scatter it, giving a softer appearance. The ocean surface often combines both types. Ripples break up the image while calm areas mirror the sky perfectly. Even our own skin participates in both processes. The oily outer layer reflects light slightly, while deeper layers scatter it, giving human faces their characteristic glow. In contrast, refraction is what happens when light passes from one medium to another, from air into water, or from air into glass. Because light travels at different speeds in different materials, its path bends at the boundary. This bending follows Snell's law, a precise relationship between the angle of entry and the indices of refraction of the two substances. While the formula is mathematical, the effect is familiar. Place a spoon in a glass of water, and it appears bent at the surface. A swimming pool looks shallower than it really is. Through refraction, the geometry of light alters perception itself. The bending of light can be subtle or dramatic. In the atmosphere, refraction makes the sun visible a few minutes before it actually rises and keeps it shining briefly after it has set. This phenomenon, called atmospheric refraction, occurs because light rays curve as they pass through layers of air with varying density and temperature. The effect gently stretches the sun's shape near the horizon, producing those fleeting, flattened disks that mark dawn and dusk. On smaller scales, refraction is the foundation of every optical device. A lens is simply a shaped piece of transparent material designed to bend light in a controlled way. Convex lenses bring parallel rays together to a focus, allowing us to magnify or capture images. Concave lenses spread light apart, correcting for nearsighted vision. The world of microscopes, telescopes, and cameras, even the focusing of light within the human eye, all rely on this same principle. Every time you adjust a pair of glasses or focus a camera, you are harnessing refraction to guide photons precisely where they need to go. Reflection and refraction often work together, creating some of nature's most familiar beauty. When sunlight strikes water, part of it reflects, forming a glint or glare, while the rest refracts beneath the surface, bending and scattering to create luminous patterns on the seabed. Those rippling lines that dance across the bottom of a pool, called caustics, are formed by converging rays refracted through the moving surface. In a single moment, light performs both actions, revealing how motion and geometry can transform simple physics into art. Every transparent material tells a story of these interactions. Diamonds sparkle because their high refractive index bends light sharply, forcing multiple internal reflections before it escapes. Raindrops do the same on a larger scale, bending sunlight into rainbows as light refracts in and out while reflecting once within. Even the glimmer of a candle through glass is shaped by layers of reflection and refraction blending seamlessly. On a deeper level, these phenomena demonstrate light's sensitivity to its surroundings. It responds to boundaries not by resisting but by adapting, turning, or bending according to the structure it meets. The rules are fixed, yet the outcomes are endlessly varied. From a mirror's clarity to a crystal's prism, light proves that order and grace can arise from simple laws applied again and again across the universe. Imagine standing beside a calm lake at sunset. The sky above glows with warm color, and the water below mirrors that same glow almost perfectly. Yet beneath the surface, reeds appear to bend and shift because their light refracts through the boundary between air and water. Two worlds, reflection above and refraction below, meet at a single line. You are watching physics and beauty merge in real time, the universe explaining itself through color and geometry. Reflection and refraction are the quiet architects of vision. They shape every beam that reaches your eyes, whether bounced from a leaf, bent through glass, or scattered by air. They govern how we perceive boundaries, distance, and brightness. In every glance you take, these principles are at work, invisible, constant, and elegant, translating the movement of photons into the language of sight. The control of light, bending it, reflecting it, Focusing it is one of humanity's oldest fascinations. Long before we understood the physics of optics, we learned to harness reflection and refraction for practical and symbolic purposes. From polished obsidian pools to modern telescopes orbiting the Earth, the story of mirrors and lenses is a record of our desire to see farther, to understand more deeply, and to make the invisible visible. The earliest mirrors were natural. Ancient humans discovered that still water reflected their image, a moment both startling and revealing. Later, people found that polished volcanic glass or bronze could capture that same reflection, allowing the face to be studied and adorned. These early tools carried mystical meaning. To see one's reflection was to glimpse the soul or to communicate with the divine. Even today, mirrors retain a quiet symbolism. They show us reality reversed, familiar yet subtly altered, reminding us that perception always depends on perspective. As metallurgy advanced, mirror making became an art. The Egyptians coated copper with tin, the Romans refined silvered bronze. True glass mirrors emerged in Venice during the Renaissance, where artisans learned to coat one side of glass with a thin layer of mercury or later silver. This innovation created images of unmatched clarity and brightness. Mirrors soon filled art studios and homes, expanding spaces, doubling candlelight, and symbolizing both vanity and knowledge. Each technological improvement brought us closer to perfect reflection, a surface that gives back every photon without distortion. Yet mirrors do more than reveal appearances. They guide and amplify light. A simple concave mirror can focus sunlight to a single intense point, igniting fire or concentrating energy for experiments. The same principle, scaled up, drives modern telescopes. Instruments like the Hubble Space Telescope use large, curved mirrors to collect faint starlight and bring it into focus. By perfectly shaping those surfaces, astronomers can gather light from billions of light-years away, turning reflection into discovery. In this way, a mirror is not just an object of self-inspection but a window into the cosmos. If mirrors capture and direct light, lenses transform it. The history of lenses stretches back at least 2,000 years. The ancient Greeks and Romans used spheres of glass or crystal to magnify small writing or to focus sunlight. The word lens itself comes from lentil, a nod to the shape's similarity to the seed. But it wasn't until the late Middle Ages that craftsmen began grinding glass with the precision needed for true optical instruments. In the 13th century, reading stones, early magnifying lenses, appeared in Europe, granting new life to aging eyes. From there, the art of lens making advanced rapidly. By the early 17th century, combinations of convex and concave lenses formed the first telescopes and microscopes. Galileo turned one skyward and revealed moons circling Jupiter. Leeuwenhoek turned another downward and discovered an invisible world of microorganisms. Both directions expanded the human horizon immeasurably. The science behind these instruments rests on refraction. When light enters or exits a curved lens, its path bends, converging or diverging depending on the shape. A convex lens focuses parallel rays to a single point, the focal point, making distant objects appear nearer or small details magnified. A concave lens, curving inward, spreads light apart and corrects for vision problems like myopia. Together, these simple geometries have given rise to eyeglasses, cameras, projectors, and the entire field of optical engineering. Mirrors and lenses, though based on opposite principles, often work in harmony. A reflecting telescope, for instance, uses a concave mirror to collect light and a set of lenses to focus and correct the image. Microscopes combine multiple lenses to counteract distortions. Even our eyes rely on both concepts. The cornea and lens refract incoming light, while the retina acts as a natural screen, reflecting signals inward to the brain. The devices we create are extensions of our biology, external organs of sight. The mastery of these tools has changed how we understand existence. Through mirrors, we learn to study ourselves. Through lenses, we learn to study everything else. They taught us that seeing is not passive reception but active transformation, a process of gathering, bending, and interpreting light. Each improvement in craftsmanship, from hand-ground glass to computer-polished optics, has revealed more of nature's hidden order. The telescope showed that the heavens obey physical law. The microscope proved that life thrives in the smallest places. Both instruments turned light into knowledge. If you hold a lens in your hand and let sunlight pass through, a small, focused circle forms on a surface. Within that point, hundreds of thousands of light rays converge, each bending according to immutable rules. The image may seem simple, but it contains a profound truth. With patience and precision, human curiosity can guide the energy of the universe itself. A mirror or lens does not change light's essence, it merely directs it, allowing us to see clearly what has always been there. The next time you catch your reflection or peer through glass, you are participating in a tradition that spans civilizations. The same physical principles that allowed ancient craftsmen to polish stone now allow modern scientists to photograph galaxies at the edge of the observable universe. Mirrors and lenses prove that understanding begins with observation, and that every image, whether microscopic or cosmic, starts with light taking a new path, guided by human hands. Few natural displays capture the imagination like a rainbow. It appears suddenly after rain, arching across the sky in perfect geometry, delicate yet unmistakable. Every culture has given it meaning, a divine bridge, a promise, a sign of hope, but at its heart, the rainbow is a precise demonstration of optics. It is sunlight separated, bent, and reflected inside millions of tiny spheres of water, each droplet acting as a small, perfect prism. To understand how a rainbow forms, imagine a beam of sunlight entering a raindrop suspended in the air. As the light passes from air into water, it refracts, slowing and bending according to Snell's law. Inside the drop, the light reflects once from the inner surface, then exits back into the air, refracting again as it leaves. Each color follows its own path, because wavelength determines how much it bends. Red light, with longer wavelengths, turns slightly less. Violet, with shorter wavelengths, bends more sharply. When billions of droplets perform this dance simultaneously, their combined output creates the circular band of color we call a rainbow. What we typically see is only a portion of a full circle. The rest lies below the horizon. From high altitudes or from an aeroplane, observers sometimes glimpse the complete ring, centered exactly opposite the sunday. The angular radius of the primary rainbow, about 42 degrees, is fixed by geometry, not chance. Every person's rainbow is unique. The droplets forming yours are different from those forming another observer's, even if you stand side by side. What appears shared is actually a series of individual optical alignments, recreated anew for each eye. Occasionally, a secondary rainbow appears above the first, fainter and with reversed colors. It arises when light reflects twice inside the raindrop instead of once. With each internal reflection, some energy escapes, which is why the second arc looks dimmer and more diffuse. Between the two arcs lies a darker region, known as Alexander's band, where little light emerges because of the geometry of reflection. These layered rainbows remind us that repetition in nature often reveals deeper structure, not redundancy. Rainbows also occur on much smaller scales. The thin films of oil on wet pavement or soap bubbles in sunlight display shifting, swirling colors caused by thin film interference, a close cousin of the rainbow's mechanism. Instead of refraction through large droplets, these colors result from light reflecting from the top and bottom surfaces of a transparent film. As the thickness of the film changes, so does the interference pattern, producing vivid, fluid mosaics. Both phenomena, the raindrop and the film, depend on the same fundamental truth. Light contains many wavelengths, and nature continually finds ways to separate and recombine them. In colder climates or high altitudes, a different spectacle appears: halos. These luminous rings or arcs surround the sun or moon, formed not by water droplets, but by ice crystals suspended in the upper atmosphere. When sunlight or moonlight passes through hexagonal ice prisms in cirrus clouds, refraction at specific angles creates halos typically 22 degrees from the source. Sometimes additional arcs appear, mock suns or parhelia, known as sundogs, glowing patches of color on either side of the sunday. Their light follows the same principles as the rainbow, but refracted through frozen rather than liquid water. Halos differ from rainbows in tone. While rainbows are bright and joyful, halos feel ethereal, often subtle and ghostly against thin clouds. The physics, however, is as rigorous as any experiment: precise crystalline symmetry guiding photons into arcs visible from hundreds of kilometers away. When you see a halo around the moon on a winter night, you are witnessing geometry written in ice. These optical wonders connect everyday experience with cosmic law. The same principles that split light in a droplet also explain how starlight bends through planetary atmospheres, how spectrographs decode stellar composition, and how light refracts in distant nebulae to produce colorful emission lines. In each case, interaction between light and matter translates invisible energy into visible beauty. Artists and scientists alike have been captivated by these displays. The painter J.M.W. Turner studied atmospheric optics to reproduce the brilliance of rainbows and halos in his works. Modern photographers chase them with lenses calibrated for high dynamic range, while meteorologists analyze them to understand cloud composition and temperature. What was once divine mystery has become an accessible laboratory in the open sky, and yet knowledge does not diminish wonder. If anything, understanding deepens it. Knowing that every droplet acts as a miniature prism only increases appreciation for the scale of cooperation required. Billions of particles, each obeying the same laws, creating a single, coherent arc visible for miles. A rainbow is a moment when probability becomes pattern, when countless random positions yield a structure precise enough to measure, yet delicate enough to vanish with the next gust of wind. Halos and rainbows remind us that light's path is both predictable and poetic. They are transient, emerging only when angle, moisture, and sunlight align, but their physics is eternal. Each appearance is a fresh expression of the same unchanging equations, an invitation to look upward and see mathematics rendered as color. If you ever find yourself beneath a passing storm as sunlight breaks through the clouds, pause for a moment before reaching for explanation. The spectrum arching before you is the story of refraction, reflection, and dispersion told in pure color. It is the universe bending its own light to speak in a language that needs no translation, a silent bridge between understanding and awe. Light is not only what reveals the world, it also drives the reactions that sustain it. Every living thing on Earth depends, directly or indirectly, on chemical transformations powered by photons. In the language of chemistry, light is both messenger and catalyst, a trigger that turns energy from the sun into the materials of life. From the green of leaves to the glow of deep-sea creatures, the chemistry of light weaves through every level of nature's design. The most essential of these processes is photosynthesis, the mechanism by which plants, algae, and some bacteria convert sunlight into chemical energy. At its core, photosynthesis uses specialized molecules called chlorophylls, which absorb photons primarily in the blue and red regions of the visible spectrum, while reflecting green, the color that paints Earth's landscapes. When a photon strikes a chlorophyll molecule, it excites an electron to a higher energy state. That single event begins a cascade, The excited electron passes through a chain of reactions known as the electron transport system, generating the molecules that store energy, ATP and NADPH. Later, through the Calvin cycle, this energy helps convert carbon dioxide and water into glucose, releasing oxygen as a byproduct. Every photon absorbed by a leaf is an act of transformation, energy from the sun captured, stored, and eventually used to build wood, grain, and flesh. Nearly all the energy that powers our civilization, from food to fossil fuels, traces its lineage to this process. When we burn coal, oil, or even wood, we are releasing sunlight that plants trapped millions of years ago. In a sense, every flame is a form of ancient daylight reignited. Light also interacts with chemistry beyond the realm of plants. In the upper atmosphere, ultraviolet radiation splits molecular oxygen into individual atoms, which then combine to form ozone, O3. This fragile layer of gas protects life on Earth by absorbing much of the sun's harmful ultraviolet rays. Yet the same energy that creates ozone can destroy it, showing how delicately balanced the chemistry of light can be. Too little UV in ozone cannot form, too much, and it breaks apart faster than it builds. The equilibrium between radiation and reaction is what keeps the atmosphere safe. Another luminous example lies within the living bodies of certain animals. In the depths of the ocean, where sunlight never reaches, creatures generate their own glow through bioluminescence. The chemistry here centers on molecules called luciferins, which, when oxidized by enzymes known as luciferases, emit visible light. Each photon released is the product of a specific reaction: oxygen joining with luciferin, electrons shifting, energy released as radiance. Fireflies, jellyfish, anglerfish, and countless marine organisms rely on this chemistry to attract mates, lure prey, or communicate in the dark. The light they produce is remarkably efficient. Almost all energy becomes light, with minimal heat loss, a feat still envied by human engineers. This efficiency has inspired scientists to imitate nature's luminous reactions. Photochemistry, the study of chemical changes induced by light, has grown into a vast field that influences medicine, energy, and materials science. In photodynamic therapy, for instance, doctors use light-activated compounds to destroy cancer cells selectively. In solar technology, researchers design materials that mimic chlorophyll's ability to convert photons into electrical current. Even photography, in its earliest chemical form, depended on light-breaking molecular bonds in silver halide crystals to capture images that could later be developed into pictures. In everyday life, we experience photochemistry in subtle ways. The fading of fabric left in sunlight, the tanning of human skin, or the yellowing of paper over time all result from light-altering molecular structures. The same photons that nourish plants can degrade pigments and polymers, proof that light, though intangible, holds immense chemical power. To manage this energy, we coat surfaces with protective films, use tinted glass, and engineer molecules designed to resist photodegradation. Controlling light's chemical influence has become a central part of modern materials science. On a molecular level, light initiates change because it transfers discrete quanta of energy. When a photon is absorbed, its energy promotes an electron to a higher orbital, altering the distribution of charge within a molecule. This shift can weaken bonds, making new reactions possible. The key is precision. Too little energy and nothing happens. Too much and the molecule is destroyed. Nature's mastery lies in matching each reaction to the right wavelength. Chlorophyll uses visible light. Ozone formation depends on ultraviolet, and infrared energy warms molecules without breaking them. Each color of light corresponds to a distinct range of chemical potential. To think of light as chemistry is to recognize that radiance is not just appearance but process, a continuous conversation between energy and matter. Every color you see is evidence of an interaction at the atomic scale. Absorption, emission, or reflection shaped by electron behavior. When sunlight strikes a leaf, a gemstone, or your own skin, photons are entering a network of reactions that transform the world molecule by molecule. In that sense, light is life's quiet architect. It builds, breaks, and rebuilds with endless patience. It powers the engines of cells, paints the oceans with luminous creatures, and maintains the fragile chemistry of our atmosphere. To study it is to see energy at work in its purest form, invisible hands assembling the visible world. Among all the ways light interacts with matter, none is more personal than the act of seeing. Vision transforms photons into perception, converting physical energy into thought. It is a chain of precision and delicacy, a journey that begins when light enters the eye and ends when the brain creates an image of the world. Understanding this process means tracing how biology and physics merge to turn illumination into awareness. Light first passes through the cornea, the transparent outer layer of the eye. The cornea provides most of the eye's focusing power, bending incoming rays toward a single point. Behind it lies the aqueous humor, a clear fluid that maintains pressure and nourishes surrounding tissues. The next gate is the pupil, a round opening controlled by the iris, whose circular muscles expand or contract to regulate how much light enters, narrowing in bright sun, widening in dim conditions. Every adjustment happens automatically, balancing sensitivity and protection with astonishing speed. After the pupil, light travels through the lens, a flexible, transparent structure whose curvature changes to focus images at varying distances. Tiny muscles called ciliary bodies contract or relax, altering the lens's shape, thicker for nearby objects, thinner for faraway ones. This process, known as accommodation, keeps the world sharp despite constant motion. As light exits the lens, it passes through the vitreous humor, the gel-like substance that fills the eye's interior, before striking the retina, the thin, light-sensitive layer lining the back of the eye. The retina is where physics gives way to biology. It contains two primary types of photoreceptor cells, rods and cones. Rods, numbering about 120 million, are highly sensitive to faint light but cannot distinguish color. They allow us to see at night and detect movement in the dark. Cones, about 6 million in number, function best in bright light and come in three varieties, each tuned to a different range of wavelengths, roughly corresponding to red, green, and blue. Together, they allow us to perceive the full spectrum of visible color through combinations of stimulation. When a photon enters the retina and strikes one of these cells, it triggers a molecular reaction. The key molecule is rhodopsin in rods and similar pigments in cones. Each contains a light-sensitive component derived from vitamin A, called retinol. When retinol absorbs a photon, it changes shape, a transformation from a bent to a straight configuration. That small structural shift alters the protein's electrical properties, setting off a cascade of biochemical signals that ultimately generate an electrical impulse. This impulse travels through a network of retinal neurons to the optic nerve, the highway that carries visual information to the brain. What follows is interpretation. The brain does not receive pictures but pulses, patterns of nerve activity representing brightness, contrast, and color. Within milliseconds, these signals are processed in the visual cortex, where they are combined, compared, and refined into an image. The brain compensates for the blind spot where the optic nerve exits, fills gaps, adjusts for motion, and even corrects color balance based on context. Vision, therefore, is not merely seeing. It is an act of construction guided by both data and expectation. The eye's design reveals how evolution has refined physics into art. The curvature of the cornea, the alignment of the lens, and the placement of receptors all conform to optical laws. Yet the system is far from perfect. Human eyes have aberrations, distortions, and limitations that camera lenses strive to eliminate. We cannot focus simultaneously on near and far objects with complete clarity, nor can we detect ultraviolet or infrared light, though many animals can. Birds, bees, and reptiles often see in ranges beyond ours, perceiving patterns and contrasts invisible to humans. What we call the visible world is only a slice of what exists. Still, our limited range is sufficient for the life we lead. The brightness of daylight, the green of vegetation, and the blue of the sky all fall precisely within our visual sweet spot. This is no coincidence. It is the result of adaptation to the spectral qualities of sunlight that penetrate Earth's atmosphere. Our eyes evolved under this light, tuning themselves to its composition. We see what our environment most abundantly provides. Beyond its biological function, vision carries deep psychological and cultural meaning. To see clearly has always symbolized understanding. In art and language, light represents knowledge, darkness, ignorance. The eye stands as a universal emblem of awareness, from Egyptian hieroglyphs to Renaissance paintings. Even in science, the telescope and microscope, extensions of our eyes, are instruments of insight as much as of observation. Consider what happens each morning when you open your eyes to daylight. Photons that left the sun 8 minutes earlier enter your pupils, traverse the transparent layers of your eyes, and are absorbed by receptor cells that send signals racing toward your brain. Within a fraction of a second, those signals become form and color, texture and depth. You are not simply witnessing light, you are participating in its final transformation, from energy into experience. In that moment, physics, chemistry, and biology converge seamlessly. Light that once streamed from a star now becomes thought, awareness, memory. The act of seeing closes the grand loop of illumination that began at the dawn of the universe. Through your eyes, the cosmos looks back upon itself. The same photons born in fusion or scattered from matter, now giving rise to consciousness that can ponder their origin. Vision is, quite literally, the universe perceiving its own light. When sunlight reaches the sea, it begins another transformation. The ocean is both a mirror and a filter, reflecting part of the light that strikes its surface while swallowing the rest. Within its depths, the radiance of the sun fades layer by layer until only darkness remains. Yet even there, light persists in unexpected forms, created not by the sun but by life itself. The story of light in the ocean is a story of change, from blinding brilliance to spectral twilight to living glow. At the boundary where air meets water, sunlight faces its first challenge. The sea's surface reflects roughly 5 to 10% of incoming light, depending on angle and calmness. On a tranquil day, the water can act as a vast mirror, returning the sky's blue back to itself. But when waves rise, the same light scatters chaotically, breaking into countless sparkles. The rest of the light penetrates the surface and begins its descent, where absorption and scattering quickly alter its color and intensity. Water is selective in what it allows to pass. Red, orange, and yellow wavelengths are absorbed within the first few meters, leaving the environment dominated by blue and green. That is why shallow tropical seas shimmer turquoise, while deeper regions turn indigo or even black. By about 200 meters down, less than 1% of surface sunlight remains. Below 1,000 meters, the aphotic zone, sunlight disappears entirely. What remains is a silent, perpetual night. This vertical gradient defines life in the sea. Near the surface, in the euphotic zone, photosynthesis flourishes. Microscopic algae and cyanobacteria, collectively known as phytoplankton, capture sunlight much like land plants do, forming the base of the oceanic food web. Their productivity sustains nearly all marine ecosystems, generating roughly half of Earth's oxygen. Every breath you take is a quiet gift from the chemistry of sunlight working just beneath the waves. As depth increases, sunlight weakens and life adapts. Fish and invertebrates of the mesopelagic zone, between about 200 and 1,000 meters, live in constant twilight. Here, vision is specialized. Many species have enlarged, sensitive eyes tuned to blue light, the last wavelength still able to penetrate so far. Some, like lanternfish and hatchetfish, also produce light of their own, a phenomenon called bioluminescence. Tiny organs, known as photophores, line their bodies, emitting controlled flashes used for communication, camouflage, or hunting. The chemistry behind this living light is elegantly simple yet astonishingly effective. It relies on the reaction between luciferin, a light-emitting molecule, and luciferase, an enzyme that facilitates the process. When oxygen is added, the reaction releases energy in the form of visible photons, often blue-green, matching the color that travels farthest in seawater. Because the reaction produces almost no heat, bioluminescence is one of nature's most efficient energy conversions. In the depths, efficiency means survival. Go deeper still, into the bathypelagic and abyssal zones, and bioluminescence becomes the dominant form of illumination. Here, light is no longer an external force but an internal invention. Organisms use it as signal and weapon. The anglerfish dangles a glowing lure to attract prey. The vampire squid releases pulses of light instead of ink to confuse predators. Tiny crustaceans flash in rhythmic patterns that may synchronize with others of their species, turning the darkness into a silent Morse code. Each spark is a brief conversation written in light. Scientists exploring these realms with submersibles often describe an overwhelming sense of awe, as if the stars themselves had sunk into the ocean. When a remotely operated vehicle moves through the dark, the disturbance of the water triggers countless bioluminescent flashes. For a few moments, the sea becomes a galaxy of living constellations. The resemblance is not coincidence. In both cases, light emerges from energetic reactions converting matter into radiance. Even in the absence of sunlight, life's bond with light endures. The energy that fuels deep-sea ecosystems ultimately originates from the sun, stored first in sinking organic matter or transported by ocean currents. Yet the creatures of the deep have redefined illumination as a language of survival. Where surface light ends, biological ingenuity begins. If you imagine descending through these layers, you could trace the fading of colors like a slow symphony in reverse. Reds vanish first, then oranges, then yellows, until only blue remains. Finally, even that fades, replaced by pinpoints of living glow, isolated, deliberate, alive. Light here is precious and purposeful. Every photon counts, every spark a statement against the dark. The ocean, then, is not merely a reservoir for water but for light's many transformations. It absorbs, scatters, creates, and reflects, turning radiation into rhythm and color into code. From the glint on the surface to the glow in the abyss, light shapes every level of marine existence. It tells us that even in places untouched by the sun, illumination finds a way to endure. Proof that life, wherever it persists, carries a fragment of brightness within itself. Long before cities blazed with electricity, before candles and oil lamps, before glass and mirrors, there was fire. It was humanity's first true command over light, a transformation of energy that could be summoned at will. Fire changed not only how people saw the world, but how they lived within it. It extended the day beyond sunset, offered warmth and protection, and became a source of ritual, invention, and community. In the language of evolution, The mastery of fire marked the moment when humans first learned to generate their own light. Fire is a chemical reaction. Combustion, a rapid combination of fuel with oxygen that releases heat, carbon dioxide, and water vapor. The process begins when energy, usually from friction or lightning, raises a material's temperature until its molecules break apart and react with oxygen. Once ignited, the reaction becomes self-sustaining. Heat from burning fuel ignites nearby material, and the chain continues. The visible glow comes from tiny particles of soot heated to incandescence and from specific atomic transitions in the gases themselves. The colors in a flame, red, orange, blue, reveal its chemistry and temperature. A candle's lower blue base is the hottest region, where fuel burns completely. The yellow tip radiates from glowing carbon particles suspended in air. From a physical perspective, firelight is an elegant balance between blackbody radiation and emission spectra. The spectrum of a typical flame spans the same range as sunlight but peaks in the red and yellow, which is why it feels warm and intimate. The brightness of a hearth is enough to illuminate faces but not overwhelm the eyes, creating a space where detail softens and distance disappears. For tens of millennia, this was the human evening, a ring of flickering light surrounded by darkness. Anthropologists estimate that controlled use of fire dates back at least 1 million years. Traces of ancient hearths, ash layers, and charred bones show that early humans not only captured fire from natural sources, but eventually learned to make it themselves. The ability to ignite flames on demand was revolutionary. Fire made food safer and easier to digest, helped ward off predators, and allowed migration into colder climates. But equally important, it changed human behavior after sunset. Around the fire, people gathered to cook, tell stories, and plan hunts. The circle of light became the first classroom, the first stage, the first sanctuary. The chemistry of combustion also connected humanity to the broader story of light in the universe. Fire transforms chemical bonds into photons, converting stored solar energy, once trapped in wood or grass through photosynthesis, back into radiant form. Each flicker of flame releases sunlight captured long before, returning it to the sky. In that sense, every campfire is a reunion between Earth and its star, an echo of photosynthesis reversed. Firelight's influence on perception and culture is profound. It shaped art, religion, and technology. Ancient cave painters in Europe used torches and stone lamps filled with animal fat to illuminate walls while they worked, their moving flames making painted figures appear to dance. In myth, fire is divine, stolen from the gods by Prometheus, guarded by hearth deities, used as symbol of purity and rebirth. In nearly every tradition, to hold light in the darkness became a metaphor for knowledge, civilization, and spirit. Scientifically, firelight was also humanity's first laboratory of optics. Observing how flames flickered and shadows moved, early thinkers began to understand how light travels and interacts. The discovery that heat and light are linked emerged from these everyday encounters. The invention of pottery, metallurgy, and glass all began with fire, processes that required understanding and controlling temperature, color, and fuel. Each innovation brought greater command over matter, and with it, over light itself. Even today, firelight retains its ancient power. A candle's flame or a campfire's glow still draws people close, slows conversation, and evokes reflection. The movement of the flame, constant yet unpredictable, engages the eyes in a way no static light can. Studies show that watching fire lowers heart rate and fosters calm, perhaps echoing the security our ancestors once felt in its warmth. Modern light sources may be brighter and cleaner, but none carry the same emotional gravity. If you watch a flame carefully, you are witnessing chemistry and history combined. Every flicker represents countless reactions occurring at once, molecules breaking apart electrons leaping, photons streaming outward. The energy that left the sun centuries ago, absorbed by a tree, is released once more as visible light. In that glow, the cycle of energy completes itself. Star, plant, human, and fire joined in one continuum. Firelight was humanity's first dialogue with the physics of illumination. It taught us that light could be born from matter, that energy could be stored and released, and that warmth and brightness could coexist. From that first controlled flame grew every other artificial light: torches, candles, gas lamps, and finally electricity. Yet despite all progress, the fire's glow remains unique. It is the original language of comfort and curiosity, the soft edge of civilization against the dark. When our ancestors gathered around their fires, they were not only warming their bodies, but also illuminating their minds. In the circle of that glow, shadows began to take shape, and ideas began to form. Firelight did not just extend the day, it began the human night, a realm of imagination lit by chemistry, sustained by wonder. When humanity first harnessed electricity, the relationship between people and darkness changed forever. Firelight had been fragile and finite, a living flame that demanded fuel and care. Electric light, by contrast, was tireless. It could be generated, controlled, and multiplied almost endlessly. It separated illumination from combustion and heat, liberating light from its ancient dependence on fire. The arrival of electric light did more than brighten the night. It redefined time, reshaped cities, and altered the rhythm of human life. The story begins in the early 19th century, when experiments revealed that passing electrical current through a thin conductor could produce both heat and light. The arc lamp, invented by Humphrey Davy around 1809, was among the first demonstrations. Two carbon rods placed close together created a dazzling white glow when electricity jumped across the gap, an electrical arc. Though brilliant, these lamps were impractical for homes. They required high current and burned out quickly. They found use mainly in lighthouses and city streets, heralding a new era of illumination that no longer depended on flame. The true revolution came later, with the invention of the incandescent bulb. In the 1872, inventors including Thomas Edison and Joseph Swan discovered that a thin filament enclosed in a vacuum or inert gas could glow for hours when electrified. As current passed through the filament, resistance caused it to heat until it radiated visible light. The vacuum prevented oxygen from reaching the filament, keeping it from burning. These bulbs were durable, simple, and safe, the first light source that could be switched on and off at will. For the first time, light became as reliable as water or air. Incandescent bulbs convert only a small fraction of their energy into visible light. Most becomes heat, yet their warm tone made them beloved for over a century. Their glow echoed firelight's warmth while freeing it from smoke and flame. The spread of electric lighting in the late 19th and early 20th centuries transformed society. Streets stayed bright after sunset, factories operated through the night, and homes became safer and cleaner. Darkness, once a natural boundary, began to retreat. Soon came refinements and alternatives. The fluorescent lamp, developed in the 1932, replaced glowing filaments with gases and phosphors. When an electric current passes through mercury vapor inside the tube, it emits ultraviolet radiation. This invisible light strikes the phosphor coating on the tube's walls, which then fluoresces, re-emitting the energy as visible light. Fluorescent lamps produced far more illumination per watt than incandescents, and lasted longer, though their color often felt colder. Their arrival filled offices, schools, and factories with a uniform brightness that became synonymous with modern efficiency. The 20th century continued the evolution with light-emitting diodes, or LEDs, first developed in the 960 seconds. LEDs operate on principles of quantum physics rather than heat. When electrons in a semiconductor recombine with positive charges, they release energy directly as photons. By adjusting the material's composition, engineers can tune the color and intensity of the emitted light. LEDs are extraordinarily efficient, converting most of their input into visible radiation, and can last tens of thousands of hours. They now illuminate everything from phone screens to entire cities, embodying humanity's most advanced control over light. Each generation of electric lighting has altered human perception. Nighttime once belonged to stars, moonlight, and flame. Now it belongs to circuitry and glass. Cities seen from orbit glow like constellations inverted, humanity's own galaxy etched on the surface of the Earth. Yet this triumph carries cost. The spread of artificial light has erased the natural darkness that shaped our biology. Many animals, from migrating birds to sea turtles, depend on cues from the night sky. Light pollution confuses them, disrupts ecosystems, and hides the stars from human eyes. Even within our bodies, overexposure to light at night can disturb circadian rhythms, the internal clocks that regulate sleep and metabolism. Scientists and urban planners are now rethinking illumination, seeking balance between safety, energy use, and natural cycles. Smart systems dim or shift color temperature after midnight, aligning streetlights closer to the hues of moonlight. Architects design interiors that mimic the daily pattern of sunlight, helping maintain biological harmony. The goal is not to extinguish electric light, but to let it coexist with darkness, to recover the rhythm that firelight once preserved. Despite its dominance, electric light retains an aura of wonder. The click of a switch, the immediate bloom of brightness, remains a small miracle. Inside every bulb or diode, electrons flow through circuits invisible to the eye, their energy transformed into countless photons that race outward in all directions. The principle is the same as in a star, energy becoming light, but miniaturized to human scale. In every lamp, we hold a controlled sun. Electricity made light democratic. It gave everyone the power once reserved for gods and firekeepers to summon brightness with a gesture. Yet with that power comes responsibility. The night does not vanish just because we can banish it. It waits behind our creations, patient and essential. Electric light is one of civilization's greatest achievements, but its truest brilliance lies in learning when to let it shine and when to let it rest. Light can be scattered, absorbed, or reflected, but it can also be organized into extraordinary order. Among all the ways humans have learned to control light, none is more remarkable than the laser, a device that turns random radiation into perfect coherence. The laser's power does not come from brightness alone, but from its discipline. Every photon aligned, every wavelength synchronized, every wave in phase. It is light made precise. The word laser stands for light amplification by stimulated emission of radiation. Though its roots lie in the theories of Einstein, who first described stimulated emission in 1917, practical lasers did not emerge until the mid-20th century. Einstein's insight was that atoms can be encouraged to emit light in unison. Normally, when an excited atom releases a photon, it does so spontaneously, producing light in a random direction. But if that photon encounters another excited atom, it can stimulate it to emit a second photon identical in energy, direction, and phase. Multiply this process millions of times inside a reflective chamber, and the result is a tightly focused beam of light, coherent, monochromatic, and incredibly pure. The first working laser, built by Theodore Maiman in 1960, used a ruby crystal as its active medium. A flash lamp pumped energy into the crystal, exciting atoms until a cascade of identical photons burst forth through a partially mirrored end. The light that escaped was narrow, red, and intensely concentrated, unlike anything seen before. Soon, other materials were discovered that could produce laser light at different wavelengths. Gases like helium-neon, semiconductors for compact diodes, and even free electron systems for extreme energies. A typical laser consists of three main parts: an energy source to excite the medium, a gain medium where stimulated emission occurs, and an optical cavity of mirrors that amplifies and directs the beam. One mirror is fully reflective, the other is partially transparent, allowing some light to escape as the output beam. The photons bouncing between the mirrors reinforce one another, building coherence with each reflection. The result is a pencil-thin ray that can remain collimated over vast distances, losing almost no intensity. This precision has countless uses. In medicine, lasers perform surgeries delicate enough to reshape corneas or remove tumors with minimal damage to surrounding tissue. In industry, they cut metal, weld microscopic circuits, and measure distances with sub-millimeter accuracy. In communication, laser pulses travel through fiber optic cables, carrying nearly all global internet data as coded bursts of light. In science, lasers cool atoms to near absolute zero for quantum experiments or trigger nuclear fusion within controlled chambers. Even the humble barcode scanner at a grocery store relies on the same underlying principle that drives research in fundamental physics. What makes laser light so unique is coherence, the degree to which waves maintain a fixed relationship with one another. Ordinary light sources, like bulbs or the sun, emit a jumble of wavelengths traveling in every direction. Laser light, by contrast, is unified. Its waves march together, crest aligned with crest, trough with trough, producing an intensity far greater than its raw power would suggest. When focused through lenses, a small laser can deliver energy sharp enough to engrave metal or vaporize stone. Coherence turns subtle energy into precision force. Yet the laser's influence is not limited to technology. It has become a metaphor for clarity and focus. To think like a laser is to concentrate energy without distraction, to direct effort rather than diffuse it. There is poetry in that comparison. Light, once thought uncontrollable, now guided by human intention into perfect symmetry. In the natural world, lasers have few parallels. Some examples exist, like the maser, the microwave equivalent, found both in laboratories and, surprisingly, in interstellar space. Certain gas clouds around stars naturally amplify microwaves through stimulated emission, creating cosmic masers detectable across the galaxy. Even in nature, coherence finds a foothold. The laser represents humanity's ongoing partnership with light, a relationship moving from observation to command. Fire gave us warmth, lenses gave us vision, electricity gave us endurance. The laser gave us precision. It is the culmination of centuries of study and imagination, transforming light from passive illumination into active instrument. When a beam leaves a laser, it appears almost calm, a quiet thread of color moving through air. But within it lies astonishing order, countless photons traveling together, perfectly synchronized, a chorus without discord. It is light disciplined into unity, and through that unity, it achieves power beyond measure. For most of history, light was simply the medium through which physicians observed illness, a source of visibility, not treatment. But as science deepened its understanding of how photons interact with tissue, light itself became both tool and remedy. From diagnosis to therapy, from microscopic imaging to life-saving surgery, medicine now depends on light in ways our ancestors could not have imagined. It has become one of the most precise and versatile instruments in healing. The first medical uses of light were observational. Before the invention of electric lamps, doctors positioned patients near windows to examine skin color, eye clarity, or the pallor of illness. Later, artificial illumination allowed surgeries to extend beyond daylight hours. Yet the true transformation began when light moved from passive illumination to active participation, when scientists discovered that certain wavelengths could trigger biological change. At the molecular level, light affects living tissue by transferring energy to atoms and molecules. When a photon is absorbed, it can excite electrons, break chemical bonds, or initiate reactions that alter cell behavior. Harnessing these effects safely required understanding both physics and biology, a partnership that gave rise to photomedicine, a field where wavelengths replace scalpels and energy replaces drugs. One of the earliest applications was ultraviolet therapy. In the early 20th century, doctors found that UV light could sterilize surfaces and kill bacteria. It remains a cornerstone of infection control today, used to disinfect surgical instruments, hospital rooms, and even the air in operating theaters. Controlled doses of ultraviolet light also help treat certain skin conditions, such as psoriasis and eczema, by slowing the overproduction of cells. Yet UV radiation's power is double-edged. It can damage DNA, leading to burns or cancer if misused. Its therapeutic value lies in careful precision. A gentler use of light emerged with phototherapy for newborns. Some infants are born with jaundice, a build-up of bilirubin in the blood that can harm the brain if levels rise too high. When exposed to blue light, bilirubin molecules break down into harmless forms the body can excrete. This discovery turned a dangerous condition into one easily treated, using nothing more than carefully calibrated illumination. The principle is simple: light alters chemistry, and chemistry restores balance. Diagnostic medicine also owes much to light. Endoscopy, for instance, uses fiber optic cables to bring illumination deep inside the body. A thin, flexible tube tipped with a light source and miniature camera allows physicians to examine organs without major surgery. The same principle drives laparoscopy, enabling precise operations through small incisions guided by glowing internal views. In both cases, light becomes an extension of vision, entering spaces once hidden. Perhaps the most striking medical partnership with light is found in laser surgery. Because laser beams can focus energy with pinpoint accuracy, they can cut, cauterize, or vaporize tissue without touching it. In ophthalmology, lasers reshape corneas to correct vision or seal damaged blood vessels in the retina. In dermatology, they remove tattoos and repair scars. In oncology, they target tumors with minimal harm to surrounding structures. What began as a laboratory curiosity now heals millions each year, with photons replacing steel. Modern imaging technologies rely on similar principles. Computed tomography (CT) uses X-rays, a high-energy form of light, to create cross-sectional images of the body. Magnetic resonance imaging (MRI), though based on radio waves rather than visible light, follows the same electromagnetic foundation. Positron emission tomography (PET) detects the gamma rays produced inside tissues to map metabolic activity. Each of these methods transforms invisible radiation into information, allowing doctors to see not just anatomy but function. Recent innovations extend even further. Photodynamic therapy (PDT) combines light-sensitive drugs with specific wavelengths of illumination. When activated by light, these compounds produce reactive oxygen species that destroy cancer cells from within, leaving nearby tissue largely unharmed. The method demonstrates how carefully tuned energy can become a selective weapon against disease. Even outside hospitals, light continues to shape health. Exposure to natural daylight regulates circadian rhythms, influences mood, and maintains vitamin D levels. Artificial lighting that mimics the daily color shifts of sunlight is now used to treat seasonal affective disorder and to improve sleep cycles in clinical environments. In every sense, light remains a biological necessity as much as a technological marvel. To watch light being used in medicine is to see precision and compassion united. A beam enters the eye, the skin, or the bloodstream, not violently, but gently, with purpose. It carries no sound, no weight, only energy shaped by understanding. From sterilization to surgery, from diagnosis to therapy, light bridges science and care. It reveals, heals, and restores, reminding us that the same energy that drives the stars can also guide a steady human hand. Long before light became a subject of physics, it was the language of art. Every painting, sculpture, and photograph begins with the artist's attempt to understand illumination, to capture how it falls, how it reveals form, and how it shapes emotion. Across centuries and cultures, artists have studied light with the same devotion as scientists, not through equations but through observation. Their discoveries, though born of intuition, often anticipated what optics would later confirm, that light is both physical and psychological, both constant and endlessly variable. In early human history, light was precious and mysterious. The flickering torches of prehistoric caves in Lascaux and Altamira not only illuminated walls but transformed them. The movement of firelight made painted animals appear to shift and breathe, a primitive form of animation. Ancient builders, too, understood light's symbolic and architectural power. Temples in Egypt, Greece, and Mesoamerica were aligned so that sunlight entered their sanctuaries at precise times of year, a celestial choreography linking heaven and earth. As civilization advanced, so did the artistic study of illumination. In the Middle Ages, light symbolized the divine. Stained glass windows in Gothic cathedrals transformed raw sunlight into a spectrum of sacred color, filling interiors with radiance that seemed unearthly. Each fragment of colored glass refracted sunlight into scenes of saints and angels, bathing worshippers in theology rendered as wavelength. For those who entered such spaces, light was more than physics, it was revelation. During the Renaissance, artists began to approach light scientifically, even before formal optics existed. Leonardo da Vinci studied how light scattered and softened with distance, describing sfumato, the blending of tones to mimic the haze of atmosphere. Caravaggio, in the 17th century, used intense contrasts of brightness and shadow, known as chiaroscuro, to heighten drama and focus the viewer's gaze. His paintings were experiments in perception, manipulating how light directs attention and defines mood. In Northern Europe, Johannes Vermeer captured daylight filtering through windows with such precision that modern physicists have analyzed his compositions to understand how he achieved their subtle realism. The invention of artificial light brought new possibilities. In the 18th and 19th centuries, gas lamps and later electric bulbs changed not only how artists worked but what they depicted. Impressionists like Claude Monet and Pierre-Auguste Renoir painted outdoors, capturing the transient interplay of sunlight and atmosphere. Monet's series on Rouen Cathedral, painted at different hours, showed how the same stone facade could shift from gold to violet within minutes. Light became time made visible. As photography emerged in the 19th century, artists began to paint with actual light. Early photographers such as Louis Daguerre and Henry Fox Talbot realized that exposure itself was a record of photons striking a surface. Chemistry turned to memory. Later, film and digital sensors refined this process, allowing light to write directly upon silver or silicon. The camera's lens became an artificial eye, guided by the same laws of refraction and focus as the human one. In modern and contemporary art, light ceased to be merely a subject. It became the medium itself. Artists like James Turrell and Olafur Eliasson use controlled light to shape perception directly, constructing immersive environments where illumination defines space. In Turrell's installations, subtle gradients of color alter depth and dimension until walls seem to dissolve. Eliasson's large-scale works, such as the Weather Project, fill vast halls with artificial suns, inviting viewers to experience the psychological warmth and awe of daylight indoors. Here, light is both material and message. Science and art intersect strongly in this realm. Understanding reflection, absorption, and color temperature allows modern artists to craft experiences that engage not only sight but emotion and physiology. Museums calibrate light intensity to preserve pigments while maintaining natural appearance. The concept of color rendering index, CRI, a measure of how accurately a light source reveals colors, bridges engineering and aesthetics, proving that even technical illumination must answer to human perception. At its heart, artistic exploration of light mirrors scientific curiosity. Both seek to reveal truth, one through reason, the other through feeling. A scientist measures wavelengths, an artist translates them into meaning, yet their goals converge to show how light shapes reality. The warmth of firelight on skin, the cold blue of dawn, the harsh glare of noon, each carries an emotional frequency as real as its physical one. If you walk through an art gallery and watch how light strikes a canvas, you witness centuries of dialogue between photons and imagination. Every reflection, every shadow, every glint of highlight is a negotiation between material and energy. In art, light is never static. It breathes, moves, and defines space. It transforms pigment into life and perception into emotion. The artist, like the physicist, knows that to study light is to study ourselves, for how we see determines how we understand what it means to be illuminated. Throughout history, light has symbolized more than vision or warmth. It has stood for spirit, wisdom, and the invisible bond between the material and the divine. Long before photons were measured and waves described, human beings sensed that illumination carried meaning beyond physics. Across every culture and era, light has been linked with life, consciousness, and transcendence, a bridge between what we can see and what we can only feel. Ancient civilizations gave light sacred origin. In Egypt, the sun god Ra sailed across the sky each day and descended into the underworld each night, reborn with dawn. To the Greeks, Helios drove his golden chariot, and to the Persians, light represented truth itself, embodied in Ahura Mazda. In Hinduism, the festival of Diwali celebrates the victory of light over darkness, knowledge over ignorance. These stories differ in detail but share a single intuition, that light is not merely something the eyes perceive, but a living force connected to awareness and creation. Science would later redefine these myths, yet the metaphor endures because it captures an essential truth. Light gives meaning to existence. Without it, color, form, and motion vanish. In darkness, the world loses coherence. Philosophers from Plato to Descartes used light as a metaphor for understanding. To see clearly became synonymous with wisdom. Even the language of modern discovery retains this symbolism. We speak of enlightenment, illumination, insight, all metaphors drawn from the same source. Religious art and architecture have long treated light as substance rather than decoration. In Gothic cathedrals, light was divine geometry made visible. Colored windows transformed sunlight into radiance that seemed to emanate from within the stone itself. Islamic mosques, with their intricate latticework, allow sunlight to fragment into patterns that shift with time, echoing the rhythm of prayer. In Buddhist temples, the flicker of candles before statues of the Enlightened One reflects inner stillness. Across traditions, illumination symbolizes connection between the finite and infinite, the visible and the eternal. The relationship between light and spirit is also psychological. Exposure to daylight profoundly affects mood, circadian rhythm, and even emotional well-being. In this sense, light literally sustains the inner world as much as the outer. Scientists studying seasonal affective disorder, SAD, found that the lack of winter sunlight can induce melancholy, while exposure to bright, full-spectrum light restores equilibrium. The old metaphor of light as joy or hope is therefore not just poetry, it is biology. In modern philosophy and science, light continues to represent knowledge at the edge of mystery. Albert Einstein described light as the measuring stick of the universe, the one constant linking time and space. Yet even he acknowledged its paradoxical nature, both wave and particle, continuous and discrete. In a quiet way, this duality reflects the human condition. Matter and spirit, logic and wonder, coexisting within a single reality. Light obeys precise equations, yet its presence still feels transcendent. Artists, poets, and scientists often converge here. The painter Turner dissolved form into light, reducing landscapes to pure radiance, as if seeking the boundary between perception and revelation. The poet Rumi called light the language of love. In quantum theory, photons act as messengers, mediating all electromagnetic interaction. Each field, artistic, spiritual, and scientific, describes the same phenomenon through different vocabularies. Whether one speaks of grace, beauty, or electromagnetism, the experience is the same. Light unites what seems divided. There is also a contemplative dimension to illumination. Many meditative traditions describe enlightenment not as acquiring new knowledge, but as seeing clearly what has always been present. In those moments, light ceases to be external and becomes internal, a recognition of awareness itself. The image of an inner flame or shining mind appears in texts from ancient Greece to Zen Buddhism. It represents consciousness, observing its own radiance. Perhaps that is why humans have always been drawn toward brightness, the candle in the dark, the sunrise after storm, the glow of stars across vast distances. Light touches both retina and reason, but it also stirs emotion, awakening something beyond measurement. It reminds us that existence is not merely matter arranged in form, but energy constantly expressed as perception, insight, and awe. In every era, people have stood beneath the same sky and felt a quiet connection between outer light and inner awareness. Whether understood as divine, natural, or quantum, light continues to symbolize what is most elusive, yet most essential: the impulse to know, to feel, to be alive. In its steady, silent way, it links the smallest atom to the highest thought, revealing that illumination, physical or spiritual, is the thread that binds all understanding. Among all the connections between light and the universe, none is more profound than its bond with time. Every ray of light carries a record of when and where it was born. To see, therefore, is always to look backward. The glow of a star, the reflection from a mirror, even the light striking a leaf, all tell stories that began moments or eons ago. Light does not simply move through time, it defines how time itself is measured. The relationship was first revealed when physicists realized that the speed of light is constant. No matter how quickly an observer moves, that velocity never changes. This simple truth led Albert Einstein to reformulate our understanding of the cosmos in his theory of relativity. Because the speed of light is fixed, time and space must adjust around it. When an object approaches that speed, time slows for it relative to a stationary observer, and distances contract along the direction of motion. Light, in this sense, is the universal yardstick, unchanging, absolute, and woven into the structure of space-time itself. To visualize the bond, imagine a photon leaving the surface of the sunday. In our frame of reference, it takes about 8 minutes to reach Earth. But, from the photon's perspective, if it could have one, no time passes at all. Traveling at light speed, the distance between emission and arrival collapses to zero. For that tiny quantum of energy, emission and absorption are simultaneous events. Light, therefore, occupies a peculiar state. It exists within time, yet experiences none of it. Astronomers rely on this property to explore cosmic history. When they observe a galaxy 10 billion light-years away, they are witnessing it as it existed 10 billion years ago. Each photon has journeyed through expanding space since before Earth formed, carrying within it information about that ancient moment. In this way, light functions as a time capsule, preserving the past with perfect fidelity. Telescopes are not merely instruments of sight, they are machines for time travel, collecting evidence that the universe has been in motion since its first luminous instant. Closer to home, light remains humanity's most precise clock. The atomic clock, which defines the international standard for time, uses microwave frequencies corresponding to the energy transitions of cesium atoms. These oscillations, measured by counting electromagnetic waves, are so stable that the most advanced clocks lose or gain less than a second over the age of the universe. The very idea of a second is thus rooted in the behavior of light and its interaction with matter. When we measure duration, we are really counting cycles of electromagnetic radiation. Even the color of light encodes temporal information. As the universe expands, the wavelengths of ancient photons stretch, shifting toward red. This cosmological redshift is direct evidence of the passage of cosmic time. By comparing how much a galaxy's light has stretched, astronomers can estimate its distance and the era from which its light was emitted. The farther the source, the older the message. The night sky, therefore, is not a simultaneous panorama but a layered archive, each star a different chapter in the unfolding of time. Light also governs the rhythms of life on Earth. The daily alternation of sunlight and darkness synchronizes biological clocks, guiding sleep, growth, and migration. This circadian timing system operates through photoreceptors in the eye that respond to blue wavelengths, sending signals to the brain's internal pacemaker. Even without realizing it, our bodies measure time through light, adjusting hormones and metabolism to the turning of the planet. The heartbeat of daylight keeps every living system aligned with the rotation of Earth. There is a poetic symmetry in the fact that the same phenomenon revealing cosmic epochs also dictates the pace of human life. The photon that left a distant galaxy billions of years ago follows the same immutable rules as the sunlight regulating your waking hours. Light unites the incomprehensible scale of the cosmos with the intimate measure of a day. In the grand architecture of the universe, light and time are inseparable threads. One defines the other. Without light, time would have no witness. Without time, light would have no journey. Every glimmer you see is an intersection of the two, a brief instant where history becomes present. To look at the world illuminated is to stand at the meeting point of motion and memory, watching the past arrive in the form of brightness. Light may seem weightless, yet it cannot escape gravity. Though photons have no mass, they still follow the curvature of space, shaped by massive bodies. This astonishing truth that light bends not because it slows, but because the very geometry of space itself is distorted, lies at the core of modern physics. The interplay between light and gravity reveals the hidden architecture of the cosmos and demonstrates how even the most intangible form of energy must obey the shape of space-time. For centuries, scientists assumed that light always traveled in straight lines. Newton proposed that gravity might influence it, but the effect was thought too small to detect. It was Albert Einstein, in 1915, who transformed this speculation into certainty. His general theory of relativity replaced the classical idea of gravity as a pulling force with the concept of curvature. According to Einstein, Massive objects like stars and planets warp the fabric of space and time around them. Light, which always follows the shortest possible path through space-time, appears to bend when that fabric curves. The first proof came in 1919, during a total solar eclipse observed by expeditions led by Arthur Eddington. Astronomers measured the apparent position of stars near the sun's edge and found them slightly displaced, just as Einstein predicted. The starlight had been deflected as it passed through the sun's gravitational field. This experiment instantly confirmed relativity and changed how humanity saw the universe, not as a flat stage, but as a flexible continuum in which light itself could be guided by geometry. This bending of light, called gravitational lensing, is now one of the most powerful tools in astronomy. When light from a distant galaxy passes near a massive cluster of galaxies, the intervening gravity acts like a lens, bending and magnifying the background light. Sometimes the effect produces multiple images of the same object, or arcs and rings known as Einstein rings. These distortions, precisely mapped, allow astronomers to measure the mass, including the dark matter, of the lensing cluster. Thus, light reveals what cannot otherwise be seen. Gravitational lensing also serves as a natural telescope. By amplifying the light from remote galaxies or exploding stars, it enables the observation of objects that would be far too faint for even our best instruments. Some of the earliest galaxies ever detected were first noticed because their light had been magnified by a cosmic lens billions of light-years away. In this way, gravity helps light tell its own story. The influence of gravity on light extends beyond bending. It also affects frequency through a process known as gravitational redshift. As light climbs away from a massive body, it loses energy, stretching into longer wavelengths. Conversely, when it falls inward, it is blue-shifted, compressed into shorter wavelengths. This effect, though minute on Earth, becomes significant near massive stars or black holes, where the gravitational field is extreme. Light escaping such regions slows in frequency, fading as though exhausted by the climb. At the event horizon of a black hole, gravity becomes so intense that not even light can escape, marking the ultimate boundary between visibility and mystery. These phenomena show that light, though swift and elusive, is not beyond influence. It moves at a fixed speed but along a path that can twist and curve. Space itself is the guide, and gravity is its sculptor. In the vast interstellar darkness, light weaves through these invisible contours, tracing the topography of the cosmos. Astronomers reading these patterns can map the unseen, the weight of galaxies, the distribution of dark matter, even the ripples of gravitational waves. The relationship between light and gravity carries profound philosophical weight. It reminds us that nothing in the universe travels alone. Every ray of light responds to the presence of mass and energy. Even the most radiant beam must bow gently to the geometry that holds everything together. In a poetic sense, gravity gives light direction, while light gives gravity visibility. One curves, the other reveals, together shaping the universe's grand design. Imagine a photon skimming the edge of a black hole, pulled just enough to arc around it and continue outward. In that curved path lies the story of both motion and structure, space bending, light obeying, and the cosmos communicating its own shape through the language of illumination. Gravity does not imprison light, it guides it, ensuring that even the universe's brightest messenger follows the contours of its invisible frame. Every message that crosses the modern world, every phone call, image, and thought sent through the internet, travels on light. It has become the carrier of civilization's collective memory, moving data at nearly the fastest speed the universe allows. Light, once a mystery of nature, is now humanity's chosen messenger. In physics, it connects space and time. In technology, it connects minds. Information and light have always been linked. Even before electronics, light was used to signal across distances, from smoke mirrors in ancient China to beacon fires along coastlines. The principle is timeless: a modulated source, a receptive eye, and a shared code. Today's fiber optic networks operate on that same foundation, though with staggering complexity. Instead of flames or mirrors, we now use lasers. Instead of hills or towers, we use glass threads finer than a human hair. Instead of moments, we send trillions of pulses each second. A fiber optic cable carries information by guiding light through its core, using total internal reflection. The fiber's inner material has a slightly higher refractive index than the surrounding cladding, causing photons to bounce repeatedly down its length without escaping. Each pulse represents a binary digit, a 1 or a 0, forming the digital language that encodes every email, video, and call. These signals can travel thousands of kilometers with minimal loss, occasionally boosted by repeaters that amplify the light. Under oceans and across continents, an invisible web of radiance links nearly every human connection. The origin of this idea lies in understanding that light can carry not just energy but data. When we vary its intensity, frequency, or phase, we create patterns, modulations that a receiver can interpret. This concept is not limited to technology. It exists in nature too. The flicker of fireflies, the colors of flowers, and even the bioluminescent flashes of deep-sea creatures are biological forms of optical communication. The universe has long used light to convey information. Humans have simply learned to read and write in its language. The scale of our mastery is astonishing. A single modern fiber can transmit terabits of information per second, equivalent to millions of simultaneous conversations. Lasers tuned to different wavelengths can share the same fiber through wavelength division multiplexing, each color carrying independent data streams. At the receiving end, detectors made of semiconductor materials like indium gallium arsenide convert light pulses into electrical signals. In effect, every photon becomes a courier of meaning, transformed into words, images, and ideas. Satellites and free space optical links extend this network beyond Earth. Communication between spacecraft often relies on laser beams because they maintain coherence across vast distances. Future missions to the Moon and Mars will use laser-based systems capable of sending high-resolution video between planets. Light, which has crossed interstellar space for billions of years, will soon carry human voices and stories across the same cosmic void. The parallels between information and light run deeper than technology. In quantum mechanics, photons can encode information in their polarization or phase, forming the basis of quantum communication. Unlike conventional data, quantum information cannot be copied without disturbing it, a principle called the no-cloning theorem. This makes quantum light transmission inherently secure. Experiments have already demonstrated encrypted quantum communication over hundreds of kilometers, and future quantum networks may connect computers across continents using photons as the ultimate keys of trust. Even in science itself, light is the primary medium of knowledge. Telescopes, microscopes, spectrometers, and sensors all translate photons into data. Whether studying the structure of DNA or the structure of galaxies, we depend on light to convey information from the unknown to the known. Every observation begins as an interaction between light and matter, a photon absorbed, scattered, or emitted, and ends as understanding. In a philosophical sense, information is the abstract form of light. Both reveal structure, both require contrast, both define reality through difference. Just as brightness has meaning only against darkness, data exists only through distinction between states. The universe itself may be an informational construct, with photons as the messengers that maintain coherence across its expanse. The next time you open a web page or send a message, you are participating in one of the most elegant symphonies of physics ever orchestrated. Invisible pulses of light, traveling through glass and air, are carrying your thoughts to another point in space. The photons that once told the story of stars now tell the story of human connection. Light no longer merely reveals the world, it communicates it, a constant conversation between matter, energy, and mind. At everyday scales, light behaves predictably. It reflects, refracts, travels in straight lines, and follows the rules of wave physics. But when scientists began to study light at its smallest scales, they discovered a world where certainty dissolves and probability reigns. This is the quantum realm, a domain where light reveals its true dual nature as both particle and wave, and where its behavior challenges the very idea of objective observation. In quantum light, the familiar becomes strange, and the boundaries of reality blur. The journey into quantum light began at the start of the 20th century, when classical physics failed to explain certain observations. The photoelectric effect, for instance, showed that shining light on a metal surface could eject electrons, but only if the light exceeded a certain frequency. Increasing brightness without changing frequency had no effect. In 1905, Albert Einstein resolved the puzzle by proposing that light consists of discrete packets of energy, photons, each carrying energy proportional to its frequency. This revelation earned him the Nobel Prize and marked the birth of quantum theory. Photons behave in ways that defy intuition. In the famous double-slit experiment, a beam of light passing through two narrow openings creates an interference pattern typical of waves, alternating bright and dark bands. Yet when photons are sent one at a time, the pattern still emerges over time, as if each photon somehow travels through both slits simultaneously and interferes with itself. If one attempts to observe which slit it actually passes through, the pattern disappears, replaced by simple particle-like impacts. Measurement itself changes the outcome. Observation, once thought passive, becomes a participant in the experiment. This duality, the coexistence of wave and particle, is not a limitation of instruments but a fundamental feature of nature. Light cannot be neatly categorized. It behaves according to how we interact with it. In quantum mechanics, all entities have this dual character, but light makes it visible in the most striking way. Each photon is both a particle localized in space and a wave spreading across possibilities. It exists in a superposition of states until measurement collapses it into one. Reality, at the smallest scale, is not fixed but probabilistic. One of the most fascinating consequences of this behavior is quantum entanglement. When two photons are created together, for example, during a process called spontaneous parametric down conversion, their properties become correlated. Measuring one instantly determines the state of the other, even if they are separated by vast distances. Einstein famously called this spooky action at a distance, but countless experiments have confirmed its accuracy. Entangled photons act as if connected by a hidden thread outside the usual constraints of space and time. This property forms the basis for emerging technologies such as quantum cryptography and quantum computing. In cryptography, entangled photons allow perfectly secure communication. Any attempt to intercept the signal disturbs the entanglement, revealing intrusion instantly. In computing, photons can serve as qubits, quantum bits that hold both 0 and 1 simultaneously until measured. These systems promise exponential increases in processing power for specific tasks, potentially transforming fields from medicine to astrophysics. Yet the significance of quantum light extends beyond technology. It forces humanity to reconsider what it means to observe the universe. In classical thinking, the world exists independently of perception. In quantum theory, Observation participates in creation. The act of measuring defines the state. Light becomes both messenger and mediator, revealing not just the structure of matter but the limits of knowledge itself. Even phenomena like vacuum fluctuations, random flickers of energy in empty space, show that light's quantum character pervades all existence. Pairs of virtual photons constantly appear and vanish, contributing to effects like the Casimir force, a subtle attraction between metal plates caused by the suppression of these quantum ripples. The vacuum, far from being void, teems with potential light that blinks in and out of reality. To contemplate quantum light is to face a universe built from uncertainty yet governed by patterns so exact that they yield lasers, fiber optics, and the digital world. The same principles that describe the unpredictability of single photons also explain the reliability of your phone's optical sensors. From chaos emerges coherence, from probability, precision. Perhaps that is the lesson of quantum light. The smallest units of reality are not rigid, but relational. They respond to context, to measurement, to presence. Every photon embodies possibility, a tiny bridge between what might be and what is. When it strikes your eye or a detector, one outcome crystallizes from countless options. In that instant, light transforms potential into fact, illuminating not only the world around us but the hidden uncertainty at its core. Light, the first phenomenon humanity ever studied and the oldest traveler in the universe, remains far from fully understood. Even after centuries of exploration, its potential continues to expand. The future of light lies not just in brighter illumination but in subtler mastery, guiding, storing, and transforming photons in ways that may reshape communication, computation, and even our relationship with energy itself. As science and technology advance, light is moving from something we use into something we engineer. One of the most promising frontiers is photonics, the science of controlling light, as we once learned to control electricity. Where electronics rely on moving electrons through wires, photonics channels photons through waveguides, circuits, and optical chips. The advantages are immense. Photons move faster than electrons and generate almost no heat. Already, photonic components power long-distance communication through fiber optics, but the next leap will happen on microscopic scales, optical computing. In these systems, light will replace electric current as the medium of logic, performing calculations using interference and resonance instead of voltage. Researchers are developing photonic processors capable of carrying out parallel computations at incredible speeds. Such devices could revolutionize artificial intelligence, weather modeling, and genome analysis by reducing the energy needed for complex calculations. Because photons do not interact with one another easily, they can pass through circuits simultaneously without interference, enabling massive data throughput. The challenge lies in manipulating them precisely, guiding them, splitting them, and making them interact when needed. Advances in nanotechnology and metamaterials are bringing this vision closer each year. Another horizon is quantum communication, which uses single photons to transmit information with absolute security. As discussed earlier, entangled photons can reveal any attempt at interception, making their data exchange theoretically unhackable. China, Europe, and the United States have already launched experimental satellites that send quantum-encrypted signals across hundreds of kilometers. In the coming decades, a quantum internet may link laboratories, banks, and governments worldwide, secured by the laws of physics rather than human encryption. Energy generation and sustainability are also entering a new era of light. Next-generation solar cells aim to mimic the efficiency of photosynthesis, capturing not only visible sunlight but also infrared and ultraviolet energy. Materials like perovskites and multi-junction semiconductors promise to push solar efficiency far beyond current limits. Some researchers are experimenting with photon upconversion, turning low-energy infrared light into higher-energy visible light that panels can use. Others are exploring light-driven catalysis, using sunlight directly to produce fuels like hydrogen from water, a potential foundation for a clean energy economy. In medicine, future therapies may rely even more on photonics. Optogenetics already allows neuroscientists to control individual neurons with pulses of light, unlocking new possibilities for understanding and treating brain disorders. Photoacoustic imaging, which combines laser illumination with ultrasound detection, creates detailed maps of tissue deep within the body without harmful radiation. One day, microscopic, light-driven robots, tiny machines guided by laser beams, could deliver drugs or repair cells from within. Astronomy, too, is being transformed by the precision of light. New telescopes equipped with adaptive optics adjust their mirrors in real time to cancel the distortion caused by Earth's atmosphere, giving sharper images than ever before. Space-based observatories such as the James Webb Space Telescope and its successors extend our reach into the infrared, allowing scientists to see galaxies forming in the early universe. Farther ahead, laser propulsion may carry spacecraft to neighboring stars. The concept of light sails, pushed by powerful ground-based lasers, could propel small probes at significant fractions of light speed, fulfilling a dream as old as imagination, to ride the very waves of light across the cosmos. Even art and architecture are embracing the new era. Buildings that once trapped light now respond to it, using electrochromic glass that tints automatically, solar walls that glow at night with stored energy, and installations that paint cities with programmable color. In every field, the line between light as tool and light as medium is disappearing. Looking ahead, it becomes clear that humanity's future will be illuminated not by more light, but by smarter light, guided, tuned, and integrated into every system we build. The photon will serve as carrier of data, catalyst of energy, healer of tissue, and engine of exploration. In the end, the story of light mirrors our own progress, from fire to filament, from laser to quantum pulse. Each generation refines what the last discovered, and though our technologies grow more complex, the essence remains the same. Light continues to reveal, to connect, and to inspire. The future it promises is not blinding but clarifying, a steady radiance leading us toward greater understanding. Every civilization that has ever lived beneath the sun has looked upward and found the same question reflected in brightness. Where does light begin, and does it ever end? From the fires of early humans to the lasers of the modern age, our story has unfolded as a long conversation with illumination. Light has guided every step of discovery, shaped every vision of beauty, and connected every thought, from the microscopic to the cosmic. To speak of eternal light is to speak of continuity, the unbroken thread running through nature, science, and consciousness itself. Physically, light began about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons could finally travel freely. Since then, those photons have been moving outward in all directions, stretching with the expanding cosmos, carrying with them the first imprint of time. That same light, the cosmic microwave background, still surrounds us, ancient radiation that quietly fills every corner of space. It is the oldest message we can read, proof that light has been both witness and participant in everything that has ever happened. And yet, light is not confined to the past. Stars still ignite, galaxies still blaze, and new photons are born each moment as matter converts into energy. The sun, a modest star among billions, fuses hydrogen into helium, releasing photons that take thousands of years to journey from its core to the surface, and only 8 minutes more to reach Earth. When that light warms your skin, you are feeling the touch of ancient atomic collisions transformed into sensation. In every photon, there is both origin and destination, a record of transformation made visible. Over cosmic timescales, even light changes form. Some of it is absorbed by dust, re-emitted as infrared radiation, or trapped forever within black holes. Yet energy itself is never lost. It merely changes its rhythm. Every photon absorbed becomes motion, heat, growth, or thought. The radiance that once left a distant star might today exist as warmth in an ocean current, or as the energy that lets a neuron fire in your brain. In this sense, light is the most universal currency, exchanged endlessly, yet never destroyed. Humanity has learned to mirror this eternal process. We have built technologies that bend, store, and transmit photons, turning them into information and memory. A single beam of laser light can now hold millions of voices. A photon traveling through glass can carry the knowledge of centuries. Our cities gleam at night, constellations of artificial stars, reminders that the human urge to create light is inseparable from the urge to understand. We illuminate the world not to banish darkness entirely, but to explore what lies beyond it. Still, the universe reminds us that too much light can obscure as much as too little. Stars can only be seen when the sky grows dark. In the balance between brightness and shadow, both clarity and rest are found. Just as ecosystems need cycles of day and night, our minds require rhythm, moments of illumination followed by moments of stillness. The eternal light that sustains life also asks for humility, a recognition that brilliance and peace coexist best when they alternate. From the quantum flicker of a photon to the grandeur of galaxies, from the glow of firelight to the precision of lasers, the nature of light has always mirrored the nature of existence. It is both wave and particle, predictable and mysterious, ancient and ever-renewing. It flows through matter, through thought, through time itself, linking what was, what is, and what will be. When we study light, we are studying the continuity of being, the way the universe communicates its presence through energy that never truly ceases. If all the lamps of Earth were to go dark tonight, the stars above would still shine, their photons crossing unimaginable distances to find us. Some of that light left its source before humanity existed and will continue long after we are gone. In its endurance lies reassurance that illumination, in one form or another, will always persist. The cosmos began in radiance and will likely end in it, an infinite conversation of energy woven into the fabric of time. And so, as this long journey of understanding draws to a close, the same truth remains constant. Light surrounds, defines, and sustains us. It connects the heart of a star to the spark of human thought, reminding us that we are part of the same luminous continuum. We from Sleepy Stories wish you a good night.